reactor vessel and refueling operations.
Oh my goodness. So that's a nuclear...
I never get tired of that.
It's all naturally occurring. That's
Yes.
not from the plant.
That shows you how conservative we are at the nuclear plant, is we will pants you if you get a little bit too much background radiation due to static cling. It's time for some more smarter every day. Specifically, refueling a nuclear reactor, something you do every 18 to 24 months at the nuclear plant. For those of you who don't know me, I'm Tyler Folse. I'm a nuclear engineer with a little over 10 years of experience in the commercial nuclear power industry, from engineering to operations to emergency response. I don't claim to know everything there is nuclear, but I can certainly share some knowledge. Let's see.
Is that a hot rod?
It is very hot.
That's a very hot rod.
Yes.
Oh, one thing I know from doing a bunch of refueling outages is crane operators up here on the refueling bridge. They're very professional, extremely good at what they do, but they kind of speak their own language sometimes. It's fascinating.
Back up out of the water, wouldn't no longer be here. None of us up here.
Really?
Really.
Hey, it's me.
Yes, that's why you have that much shielding. You're under upwards of 23, maybe 30 feet of water between the nuclear fuel and you. Provides you all the shielding you need.
Welcome back to Smarter Every Day. I am so incredibly excited to share this video with you. I have never experienced anything like this. I've wanted to learn about nuclear power for years, but I purposefully kept myself ignorant. Like I didn't, I deep dive into aerodynamics and all material science, things like that. But nuclear power is like this thing that I didn't want to approach until the time was right. And
Well, look, I'm happy to help you out.
the time is right. We're about to learn about nuclear power by seeing it and by meeting the people who are making nuclear power. And we're going to walk inside an active nuclear power plant, not just like on any normal day. We're going to walk in to a power plant on the day that they're refueling it. They're taking old fuel rods out and putting new fuel rods back in.
So huge props to whatever site this is that allowed him to do that. And I'm not just talking about going in with a camera crew. He needs to be trained to get on the refueling bridge. There's at least a couple of levels of general employee training that's required to get you in there. There's one on all the plant policies and procedures for they let you on site in general. And that includes things like complying with security requirements, industrial safety, and nuclear safety procedures and processes. The other one is they need to train him how to be a radiological worker in order to enter the reactor containment building during a refueling outage. And there's probably some site-specific stuff and other specialized programs that he needs to do depending on what site he's going to. And that can take the better part of a couple of days to a week, depending on his experience level. There are ways to fast track it, but the point is you're not going to go in and take a 5 to 10 minute course. It's going to be a whole deal, and you're going to have to take a test, both a physical test and a practical test for dressing out in protective clothing.
And we're going to see how they do that. And it has totally demystified nuclear power for me. Like, this experience just changed how I feel about a nuclear power plant being just down the road from where I live. It's awesome. So this is what I would ask of you to do for you. If you would just watch the video as if you're there with me and we're walking around and we're asking the questions together. And
of course, and outages are a fun time because you get to see things taken apart that you wouldn't take apart while the reactor is operating. So you get to see and learn a lot of new things. That's where a lot of new operators and engineers really learn their job quickly, is by taking part in a refueling outage.
Experiencing it and give yourself some grace, because there are moments where I have no idea what's going on and I'm just asking questions. And I think it's okay.
There are some outages that you have no idea what's going on if you're experienced. So yeah, it's something you kind of have to sit back and look at the big picture project schedule and overall plan to understand. And that's talking from someone with experience. And outages are run a little different depending on where you are. So what I see here might be completely different from the site that I've worked at.
To not know what's happening and then just let it happen. And then later on in the video, we'll understand more about it. So this is a really neat experience. I hope you really enjoy it. This is unlike the access most people get to the nuclear industry. So
yes, a lot of this stuff you need to be an employee. And I'm actually, again, kind of surprised they let him do that, which is awesome. It's props to whichever site he's going to.
It's very, very special. And I want to thank the people that let this happen. This is the culmination of months of coordination.
Brown's Ferry. Okay, so the same one that he went to and got some of this training before in a previous video.
And training and people working behind the scenes to
I've never actually been inside Brown's Ferry. I just happened to drive past it, simply because I have family in North Alabama.
this very special look into a very special place. You can't just take a camera here. You have to have the proper training, and a ton of people made this happen. I'm so grateful for that. But yeah, let's go to an app.
And he's not kidding. It's a big process to get people trained, and not just him, but his camera crew also need to be trained on this as well. So however big his media team is that are actually going into the site, they all need to get trained on that as well. And there's probably various rules about what you can photograph, what you can make a video of at a nuclear power plant. It was all super strict, so there might be a lot of jumping around we see here.
Nuclear power plant and learn about nuclear power in a very real way. Let's go get smarter every day. So something's about to happen that we've been wanting to happen forever. We're going to get to go to a nuclear plant, and this is my friend Philip, who forever I've called him Jimmy Neutron as long as I can remember.
Jimmy
and the
Neutron.
thing about Philip is he's very moderate, very level. How would you say?
Not very expressive.
This is angry face. This is also his happy face. This is his excited face, and that's kind of who you want.
That's pretty realistic at the nuclear plant.
Working in a nuclear plant, I feel. Yeah?
I'm the most boring man you'll meet. I have to get extra medium shirts.
Extra medium? Okay.
Yeah, that's nuclear plant type of humor too. All right. Yeah. One of us.
George, we're going to go to a nuclear plant. You excited?
I'm so pumped.
All right. There it is over there. Where are we at, Philip?
We are leaving the training center, and you are just east of the plant.
What's the name of the plant?
This is Browns Ferry Nuclear Plant.
All right. This is the third largest nuclear plant in the United States, correct?
That's a big one. It's a 3-unit site. Bigger than the plant that I worked at, which was just 2 units.
I don't know.
Used to be the second. Now that Vogel has units 3 and 4, Vogel is the largest in Georgia, followed by Palo Verde in Arizona, and Browns Ferry would be third now.
It's one of the biggest ones.
I believe it is, but you guys have 3 units, correct?
We have 3 units. We are the only plant that has all 3 units under one roof.
That's different. One roof meaning one reactor containment building. So the design criteria would have to be that containment building could withstand all of the energy within of those 3 nuclear reactors, simultaneously depositing their energy into the reactor containment building, whether it be in form of loss of coolant accident or steam generator line breaks. So it's quite the rugged structure.
Watch your step. Yeah.
Yes, even on like steps, people walking outside, because that's where the OSHA recordables happen. It's things like people falling down the stairs and people getting their fingers jammed into a building in the office building, not in the radiological controlled area, not in the nuclear part of the nuclear plant or even the protective area. It's around the office buildings or when these sorts of things happen, because this is where people let their guard down. And hey, I mean, when's the last time you filled out a job safety plan from walking to your car or walking to your office?
At nuclear plants, I've heard, is over the top.
Oh, yeah. We have rules on how to climb a flight of stairs.
Really?
Yes, 3 points of contact. And you will be scolded by that, rightfully so, if you are not maintaining 3 points of contact.
Crazy. But people rarely get hurt, so I guess it works.
Industrial safety, the OSHA recordables, their RIF rates are at an all-time low compared to other industries due to these seriously high standards. And I'm just talking industrial safety that you see at any other facility of this size, not even the nuclear part yet.
There you go. What's up, Bill?
Hey, how are you doing?
Doing well. All right. So this is the security.
This is our Westgate house, so we get into the plant.
Okay. Cool. Sounds good. Bill, what's your deal here at the plant?
I work with the distribution shop right now. I've worked here for about 15 years. I'll spend some time in operations as a licensed operator. And
So is this where I need to cut off the camera for security stuff, or we go?
Typical career path, works his way up and becomes a licensed operator, just like I did, and now he's over a maintenance shop, the instrumentation and controls shop. That's good. A lot of organizations want to send people to licensed operator training. You get all the additional nuclear safety and nuclear management training and the experience of running the site from the control room, and then you typically transfer into management roles in other departments. For instance, I became a licensed senior reactor operator myself and did my time on shift, working rotating shift schedules, and then transitioned to a program management role using the additional knowledge and management training and experience that I got while on shift.
I'll cut the camera here. So we just went through a lot of security that I'm not allowed to show you.
yeah,
And it's
Well said.
tense. There's a lady that you'll probably see on camera here in a minute. She's got a rifle. So I feel comfortable.
Yes, that level of security is typical at a nuclear plant.
That's pretty good.
well, we want to make sure everybody stays safe while they're working here. We don't want any issues, the wrong people being here, right?
So when you come into work every day, you've got to go through that.
Yes, sir, every day.
Yep.
All right, good. All right, so Bill, what do we have here?
So these are our two buildings. You'll see the larger building over here is our reactor building. Our shorter building over here is our turbine building. Reactor building's got the reactors that are housed in there. It's really a secondary containment, just in case something went awry. And then our turbine building over here.
Primary containment, talking about the reactor vessels itself as well as the bioshielding around that. Though I'm not exactly sure what the layout of that would look like at a 3-unit site, but we're just talking about it. He's talking about additional layers of radiation protection.
We got our turbine and our generator where we produce our power. And then you can actually over here see all the lines that are coming out of the plant. That's where we supply 500,000 volts to the valley, which goes to the substations out there to our homes, really. Neutron.
The reason why you step it up to 500,000 volts, the generators themselves are probably only at about 25,000, but it's for long-range transmission. The site that I worked at the switchyard was at 345,000 volts, but the power doesn't have to travel as far. I mean, here we're talking about North Alabama, less populated area. So, yeah, I believe go ahead and set up the transmission lines to a higher voltage.
Electrons.
So the reactor's actually in there.
Yep.
And then this is the generator turbine, all this.
Yep.
And then that's where distribution. The security stuff, it's pretty serious.
I think so.
Yeah.
Yeah, it's
You take it seriously.
Am I allowed to say what we had to do to get in the building?
I mean, yeah, you can. I think so.
Biometrics.
Yeah.
Biometrics and that was, and not normal biometrics.
Browns Ferry Nuclear Power Plant is run by TVA, the Tennessee Valley Authority. It's a public corporation created during the New Deal coming out of the Great Depression to help manage and protect and use the Tennessee Valley's vast waterway system as effectively as possible. And today, it's become a major energy provider in the area, pushing power out to over 10 million people. This plant, Browns Ferry, was constructed in the 1960s and 1970s and is a huge deal for my local community. We headed down to what's called dosimetry, where we would be checked in and given devices called dosimeters that would track our exposure to ionizing radiation as we move throughout the plant. This video is a part of a deep dive series on nuclear power that we're doing here on Smarter Every Day. In a previous video, we learned about these dosimeters when George and I had to...
And if you want to see my reaction to this one, I'll put it down in a comment below. I really like this series thus far. They go into a very in-depth look at this sort of thing that most people outside the industry don't get to see. It's really good series.
Radiation training in order to enter the plant today. So if you want to go deeper into nuclear power,
This And this all makes sense. He might as well stick with the site that he did all that for the purpose of the other video. Not to mention, I think he's from the area, so it saves him from having to travel.
This series, it's pretty cool. You can subscribe on YouTube if you're into that, or you can sign up for the email list on smartereveryday.com, and when the new videos come out, I'll send them to you. In an earlier video in the series, we explored EBR-1, the first nuclear reactor to generate electricity and put it on the grid, and there's so much more that we're going to learn about in this deep dive, from how we handle radioactive materials to future nuclear technology to how to deal with nuclear waste. In upcoming videos, we're going to explore all this and learn everything we can about this important energy option. But right now, let's get back to the plant.
How's it going? I'm Destin.
Destin, nice to meet you.
Nice to meet you.
Okay, just one at a time. I'll need you to step into,
This?
yes, the DIM 5.
Okay. Sounds good.
Little room here.
And so what are we doing here? You said your name was?
Amanda.
I'm
As far
Destin, yeah.
Yes.
Background count.
Radiation protection. I'm the one that issues dosimetry.
Oh, great.
Yes. so
Awesome. So I go right in here?
Step in, face the wall, or you can.
Face the wall?
3, 2,
Be careful stepping out.
clean.
This little device, as far
You have to walk through one of those every time you leave the plant. And I say the plant, not just the radiological controlled area. There's one within there too. So if you go in the radiological controlled area every day, then yeah, you're going to be stepping through these a lot.
it's your dosimeter of legal record.
Okay.
Yep.
So when this is red, it has dose on it, and when you log in, you'll have a self-reading dosimeter. It's real time,
Okay.
okay?
And so I'll carry these with me at all times, right?
Well, when you go into the RCA, you'll log into the SRD, but this will be on your person all time,
Okay.
okay?
Got it.
Yep, you keep that on you all time, usually near your badge and on your upper body, and it's something you just keep with you, and it is designed to track chronic dose, whereas the EPD is to measure acute dose and dose you're getting while you're actively in the RCA, like she said. But your chronic dose is measured outside of the radiological controlled area, which is quite conservative. So dose that you would get essentially from your job site that's not in the normal controlled area is going to get measured. Now, you're not going to get very much from that, but still, it's another example of the nuclear industry being conservative. And you do switch those out, but it's typically every 6 months. So the Radiation Protection Office will keep track of how much dose you've received your entire career. And if you're visiting other sites, that's one thing that it takes into consideration is your radiation protection office from your site would communicate with the office from the other site just so your entire dose record is kept up. It follows you. It's kind of like your medical records.
And so do you track this for everybody in the entire plant?
Anyone who has to go in the RCA, yes.
Wow.
Yeah.
So yes, that includes permanent plant employees, contractors, and I guess I'm going to say VIP visitors that would get to go into the RCA in this case.
Okay.
About 2,000, and during an outage, it could be anywhere from there to 4,000.
Yep, that's typical, bringing in a whole bunch of extra vendors during an outage. There are people whose entire career is to go from plant to plant to assist during a refueling outage.
That's amazing. So while we're waiting on dosimetry, this is Angela.
Hi.
So what instructions did they give you?
No, they just said just to be with y'all, just in case anything happened and we needed to escort y'all out.
You're more intimidating than I expected.
Really?
You are, yes.
Thank you.
You're welcome.
Doing your job well.
Ma'am?
You can hold this.
Oh, thank you so much. So this is my dosimeter.
Dosimeter, yes.
I should feel a bond with this.
Yes.
Okay, thank
Do
you.
not lose it.
Okay, great.
Yeah,
Thank you.
you don't want
Are
to
you
lose that
excited to bond
bond.
with your dosimeter?
That's a mess. It's mostly paperwork, but it can turn into a real pain if you lose your dosimeter or if you lose your badge, anything like that. And you get escorted and at all times if you were to lose one while you were in the radiological controlled area. Basically, they escort you out just to make sure nothing else is, you don't get an unmonitored dose.
To need it.
There's a lot of stuff.
Yes.
Good thing I have 3 chins. Start clipping stuff to my chins.
And depending on where you're going to need to have FME tie-off. That's foreign material exclusion, so they don't inadvertently fall off into, say, the refueling cavity.
I have the beard.
So you have the beard? Yeah.
You excited?
I'm very excited. Did you see me do a little dance just then?
I like this guy.
Yeah.
It's good to have people excited here.
That's good. I'm seeing a lot of beards, man. I don't have a beard. Do they issue you that beard?
Yes, they do.
Mentions beards. If you're in the control room, you're not going to see any, at least the people that are licensed operators, because you need to have SCBA training, because there are SCBAs scheduled in staged by the control room, so you can be there and don your SCBA in case, I don't know, there's some sort of airborne contamination hazard. Not typical at a nuclear power plant, but who knows? There could be an accident in a nearby chemical plant. The point is, it's prepared for that you can still stay in the control room even if a hazardous atmosphere presents itself. Within reason, there are control room evacuation procedures, but yeah, one of the things, if you work in the control room, you're not allowed to have a beard, so you can still wear SCBA if you need to.
He just got a mustache. I don't have facial hair. I don't feel like I can be here.
Bill thought I might
You'd be ideal in the control room, buddy.
find it interesting to check in some of the people in the executive offices, so we went upstairs and met Lionel Locke, the safety manager.
What's up, man?
How you doing? I'm Lionel.
I'm Destin. Nice to meet you.
Nice to meet you.
Yeah, pleasure.
So Lionel, I have heard a word over and over ever since I got here, and it's outage.
Yes.
I've heard the word outage. What is it? What is an outage?
An outage means that, so the plant, when it's running, it's online. That
Okay.
means we're making power, we're putting it in the transmission system. We got to turn the plant off, cool everything down, open everything up so we can fix the valves, fix the motors, and do the maintenance of the plant. So we're not creating any power, not generating any electricity. But this is a monster. It's 3 units, and it's a challenge to manage not just the outage, the unit that we have an outage. We still have 2 reactors that are running.
Okay.
So this.
You're going to want to stagger outages so you're continuing to produce electricity at some level of capacity. At the 2-unit site I worked at, we staggered them. And based on the schedule with there, it was 18 months. So the math worked out that every 3 years you have 2 outages, both in the spring and in the fall when demand is low. You wouldn't want to have an outage during a summer or winter. But yes, there's certain types of maintenance. Not just refueling, but there's certain types of maintenance that needs to be done. It can only be done when the reactors are not just shut down, but completely cooled down and depressurized. That takes multiple days. An emergency shutdown takes a few seconds, but to fully cool down and depressurize, that takes days. And there's certain maintenance that has to be done periodically that isn't really so much as maintenance, it's more of testing that is required per federal law. So you can't defer some things during an outage. So it isn't just refuel the reactor as fast as you can. You have to do a lot of those maintenances. Those are called surveillances. And those surveillances are done in accordance with the reactor's technical specifications, which are an agreement between the plant operating company and the federal government that of how you will operate the plant safely. There's a whole section of the tech specs on surveillances.
Always a challenge, and it's a good team. It takes a solid team to manage all of this. Some of the other sites that may just have 1 unit, a little easier for them because they just got that 1 unit in an outage. That's all they got to focus on. But we're still producing power with 2 other units.
Yeah, and producing power with 2, it's usually one's online and one's off is what I'm used to. So with 2 online and 1 off, that's a bit of a different mindset. So it's like, okay, you have an outage, but you're still mostly online.
So there's 3 units. So Bill, there's 3 units here?
Yes, sir.
Okay, and so what are the unit 1, unit 2, unit 3? Is that what you call them?
Yes, sir. Yeah, each operating at about 4,000 thermal megawatts, putting out about 1,350 megawatts electric to the grid.
Each one of those are similar size to the plant that I worked at. So this one's bigger, a full 50% bigger.
What's going down for the outage?
Right now, Unit 2's down, and we're refueling that and performing all the work that Lionel discussed, and Unit 1 and 3 are operating.
We're in a refueling outage. So refueling outage means we are literally taking the spent fuel out, putting in the spent fuel pool, and we got around 330 new assemblies that we're putting inside the core. So or you have your coal plants that have railroad cars constantly coming in with coal. We can run 2 years off of off the nuclear fuel that we put in.
Okay, so 2-year fuel cycle here. Good. That's better than 18 months. That also works better when you have 3 units. The math would work out a bit better for keeping 2 units offline or online.
For this outage.
And that's happening today.
Right now, as we speak.
So this is a big day to be here.
Yes, it is.
And this is why you brought me in on a Saturday.
I did, yes, sir.
Thank you so much, man.
Oh, yeah. The whole 9 to 5, Monday through Friday. Yeah, that's not a thing during an outage. A typical schedule during an outage, at least when I worked, was 4 on, 1 off, whether it be day shift or night shift, and it would be 12 hours. So you'd get quite a bit of overtime. Of course, since I was in management, I didn't get the time and a half pay, but hey, to each their own.
Lionel, thank you.
Appreciate it.
Is this a fuel bundle, Bill?
Yeah, actually, that is a mock-up of a fuel bundle.
So
Yeah.
this is what we're refueling today?
That's right. Yeah, this is a Natrium 11, I believe, is a style on this one.
Okay.
These are your fuel rods. You got a good view of the fuel pellets here, also.
So these
yeah.
are the pellets. All right, and so we're pulling these things out with a crane and putting them back in?
Correct. Yeah.
So these fuel rods are where the magic happens, and I want to talk about.
So one thing is they mentioned 330 of them. The plant that I worked at, the number was 193, but these fuel rods are a little smaller, and that's typically for boiling water reactors versus pressurized water reactors. So ultimately the weight, the power generation is all about the same, but they're a little smaller in boiling water reactors.
So much. Someone actually sent me a book after one of the first videos in this series. I opened the book. It's made like a long time ago.
Of course.
Sure enough, the exact reactor for Browns Ferry Nuclear Power Plant is in there. Look at that. Those are the fuel bundles. And I have been researching this so much. The thing specifically.
And yes, when I went to school, you use textbooks that are about that old, and they were old when I went to school, using stuff from like the 70s, because that's when a lot of this stuff was designed.
Talk about is the difference between a boiling water reactor, which is what Browns Ferry is, and a pressurized water reactor.
Which is
but we
where I
just
work.
don't have time for that in this video. In a future video, we're going to talk to an internationally recognized expert named Bill Williamson. This guy knows so much. We are going to learn this stuff, but this video is just not the place to do it. But for now, let's go talk to the guy that's over this nuclear power plant.
Trying to hide from us? I got some people that wanted to meet you, Quinn.
What's up, Quinn?
Hey man, good to see you.
How's it going?
Good.
Yeah. So I'm Destin.
Yeah.
Yeah. We met during my training, right?
Yeah.
That's not uncommon, the plant manager's office not having any windows.
All right, so I met Lionel, so far safety guy, and you're the plant manager, right?
Correct.
So I learned about the outage. So we're in an outage.
Yep.
Unit 2 is down. Is that what that means up there?
Yeah. So one of the benefits of the plant manager's office is you have megawatt meters for all 3 units.
Is that real?
Yeah.
Absolutely real? Okay.
Okay, that's a little different. I haven't seen that at any other plant manager's office. I mean, really, that's as far as who's actually responsible for that. I mean, yes, the plant manager, all the operating crews would report to the plant manager, but it's really going to be the shift manager of each operations crew that really oversees each megawatt. But for the longer strategic vision, yes, it's still going to be the plant manager's job, but I've never seen these meters in a plant manager's office before.
You can see 2 is down, 1's at 100% power, 3 is right at about 91% power right now.
I don't know, I might want to get those looked at. It looks like Unit 2 there is producing negative, which it could actually be using some electricity, but obviously you wouldn't see it there to run all the systems, the support systems and auxiliaries while the unit is down. I'm not sure what phase in the outage they are, at least as far as the secondary plant is concerned.
We're coming back up to 100 from the outage that we talked about.
Okay, so how long does it take to come up to, what is 100% in terms of megawatts?
About 1,300 on a good cold river day.
Okay, he's talking about on the grid specifically, which is different from the reactor. The reactor is going to be closer to 4,000.
What do you mean by cold river day?
So when the river's cold, it allows us to improve our vacuum in the condenser, which improves our megawatt output.
So really, a nuclear power plant is a big Carnot-style heat engine. Carnot being the ideal case, of course. But how you improve your efficiency is you make your T hot, which is the reactor, hotter, or you make T cold, which is the reservoir, in this case the Tennessee River, colder. So That's why he's talking about on a cold day, yeah, you get a little bit more thermodynamic efficiency from this place.
Really? Yeah, it's temperature dependent.
So tell me, when you see these dials up here like this, what does that make you feel? Like, is
The one on the left makes me happy.
okay? Yeah.
And the one in the center is expected, right? So you have to, every 2 years, you have to take a unit down to change out a third of the nuclear fuel. And that's what we're doing. That's what you'll go see here in a little bit. So they're moving fuel in and out of the core.
And the one on the far right, are you comfortable with that?
No, I like it to match the one in Unit 1.
So what I've been told is that
So Unit 3 is not at 100%. Interesting. Could be something else going on.
nuclear plants, like, you want it to be boring.
Yeah, absolutely. Absolutely. Hot, straight, normal, 100% power, just sit there.
Really? So steady state.
Yep.
Steaming and dreaming.
How long does it take to bring a plant down for an outage, and then versus how long does it take to bring it back up?
So the way we do it for refueling outages, it takes about 12 hours. We start around 9 o'clock in the morning, derating in steps, and then we can go in at various. So
this is your slow, non-emergency, controlled ramp down, not a reactor trip from 100% power.
WR, which is boiling water reactor, which means we have contaminated systems throughout the whole station. So there's areas that we can't access at 100% power that we can't access at 40% power.
So the difference he's getting at is boiling water reactors. So boiling does occur within the reactor vessel, and it's hydraulically coupled to the secondary part of the plant. So yes, you're going to get some trace amounts, and I say trace relative to the intensity of a nuclear reactor that you would get in the secondary or turbine part of the cycle, in contrast to a pressurized water reactor, which is going to be separate. So there's not as much cleanup you have to do to the secondary turbine side of a pressurized water reactor. It's one of the advantages of pressurized water reactors over boiling water reactors.
We'll go in at 40%. We'll come down from, like this last time we were coasting, we were down around 80% power because our fuel was running out. So we were coasting down from 100 down to 80. And then we started our outage, so we came down to around 40.
That's typical. In a way, that's actually good, because that means you probably didn't have to take a forced outage. They keep saying refueling outage, but a forced outage is you had to trip the reactor for some reason. And at that point, your goal is basically to get the unit back up to 100%, fix whatever broke, and get it back up to 100%. There's also the term maintenance outage that's thrown out there, and usually it's going to be coupled with a refueling outage, and sometimes you'll just have a longer outage. A lot of refueling outages are typically done with a span of 30 days, but some longer maintenance outages, say you're replacing a steam generator, that could take something like 60 or even 90.
Percent power, took heaters out of service, did some inspections, looking for leaks, looking for stuff we would need to fix during the outage.
He's talking about feed water heaters that preheat the secondary part of the nuclear plant.
So that we had the right scope for the outage.
So you start ramping down.
Right.
You take an assessment because you can go more places.
That's right.
And then at that time, you start planning for the outage. Do you keep it at 40%?
No, so we come down to around 20% and then insert what we call a manual scram.
Okay.
What is it?
That's going to be a reactor trip, and that's typical. You want to get less than 20%. It also eases the inertia on the system. It's the nuclear equivalent versus slamming on the brakes at 20 miles per hour versus slamming on the brakes at 100 miles per hour. You're way less likely to break something.
So there's two big red buttons in the control room. You can see those. An operator pushes those, and all the rods go.
At the plant I worked at, it was a pistol grip switch that you turn like a key.
BWR, they come in from the bottom. Anyway, so
bottom water reactor. Not really.
Immediately shuts down the reactor.
Okay, so what is a BW?
Yeah, we're talking less than 2 seconds.
So boiling water reactor means it's designed to have boiling inside the reactor vessel.
Okay.
In a pressurized water reactor, you're not supposed to have that. But no, it doesn't. And there are various stages of boiling, so you're talking about full bulk boiling, which is probably what you mostly think of when you think of boiling once you get your tea kettle set up.
Pressurized water reactors don't have mass boiling in their reactors. They have nucleate boiling, which means tiny little bubbles form on the surface of the fuel and then immediately collapse.
Literally what happens when you're boiling a pot of water and you're watching a pot trying to make it boil for some reason, and you're just seeing the little bubbles rise and never making it to the top. So which is a lot further away when you're talking about heat of vaporization, especially at these temperatures and pressures. There's a big difference between nucleate boiling or bulk boiling or film boiling. There are various levels of boiling between nucleate and a full-on boiling water reactor.
Pressure is so high that it doesn't turn to boiling.
Okay.
Boiling water reactors are at a mere 1,000-ish psi compared to a pressurized water reactor at about 2,250 when you're fully pressurized.
Essentially are at saturation conditions inside the vessel. So we run around 1,000 pounds, 1,000 psig, which equates to what, about 570 degrees.
Yeah.
So even though it's called a boiling water reactor and the other one's called a pressurized water reactor, you're still boiling under pressure here.
Yeah. But we're designed.
You want it to be hot enough that you actually make something worthwhile. Again, back to the Carnot example. You're just around saturation versus being subcooled.
Mass boiling. So we have a huge pocket of steam inside the pressure vessel, which PWRs don't.
Okay. Kind of like the old locomotives, the steam locomotives, they had a big reservoir up top of steam.
Yeah, right.
Yeah.
That's right.
And so what temperature will that steam be? 570, you said?
Yeah, about 570.
Yeah, moderate temperatures.
So they're also a little colder. The steam generator, the steam is going to be comparable, but the reactor coolant system is going to be around 620, 630 core exit thermocouple temperature.
Yes, that's right.
So these are literally the steam tables.
Yeah.
Yes, you have to get those out, and you have to use these manual ones on your licensed operator exams. You can't use an app on your phone during the test. That is a requirement, and you could thank the 3 Mile Island accident for making this a requirement. Every pressurized water reactor, the 3 Mile Island scenario is going to be one of your scenarios because it's a pressurized water reactor.
Let's see. Saturated steam.
Yep. You look at the tables, and then you fold it out to look at the Mollier diagram. Because you're going to get that one question. It shows up on just about every single regulatory exam, rightfully so, because, again, that was the 3 Mile Island scenario. You're either going to get that, or you're going to get something that looks like that in the simulator. Or both. I mean, you're tested a lot.
Because every nuclear plant is just a steam plant, right?
Correct. Ultimately, you're creating steam to drive a turbine. So about 550.
So you went to...
You're just using some hot rocks.
PSI.
I like that they're including this in the video. It's great.
Square inch. You went down to 1,000, right?
Complete with it blurry, complete with the shimmer, because that's realistic. You're going to look at it, and it's going to shimmer, and trying to keep your place and keep your fingers in the right spot. That's literally the hardest part. None of this is hard at all from an engineering perspective. At least when it comes to using this, it's just losing your place. And if you're making this calculation for real, well, you don't have to just use steam tables. You can use apps in the real unit. And you're going to get a peer checker. You're going to get peer checked. So, and there's one person in the control room whose job it is to do these sorts of calculations. That's known as the shift technical advisor. Typically, which was one of the jobs I had on shift. That's pretty common. Nuclear engineer with a nuclear engineer that's also a licensed operator. You don't actually have to have a full nuclear engineering degree, but you need to have some level of educational requirement. Compared that licensed operators, you technically don't need even a bachelor's degree for that, but you would need a fair bit of on-shift time experience or equivalent military experience before that if you didn't have the educational background.
That's where this BWR operates. And then the temperature that water boils is in this area.
About 550, yeah.
About 550.
And that's a similar pressure for the steam and temperature for the steam generators. So ultimately, it's similar-ish thermodynamic efficiency. It's a different structure than the reactor vessel. The reactor coolant system is what's heating up the steam generators in a pressurized water reactor.
And so it's just physics.
Yep.
Yeah. Just
so
physics.
We're going to see Unit 2 open, which makes sense because we're in an outage.
It's flooded up too. You'll be able to see. So as a part of refueling, we take those concrete blocks off, we take the drywall head off, we take the reactor pressure vessel head off and put them on stands, and then we flood the water level up equal to the spent fuel pool, and then we remove some shield blocks, and then we just lift the fuel up, move it over, and put it down. So it's one big pool.
Thanks, Quinn.
Thank you.
That's a key point. You have additional water than what's normally kept there for additional margin, both in terms of radiological safety and in terms of heat up safety. Because a lot of this fresh fuel, it's going to be hotter than what you typically see in a spent fuel pool. It just hasn't had as much time to decay yet.
We've got some hard hats for you, some safety equipment for when you get out in the plant.
Great.
Oh, we get a lanyard.
That you do.
Bill's making me do more training. What am I doing?
You're doing some form material training, so one of the things with the core, it's open, right? So we want to make sure that there's nothing that could potentially drop off you and fall onto the core. We have methods of retrieval, obviously. And
that's a big deal. And the reason why there's a form material exclusion program is because Fermi Unit 1 suffered a fuel damage, a meltdown, and to use the journalist terms, due to a foreign material exclusion event or an FME event. So everyone in any of these FME zones, such as above the reactor cavity during an outage, is going to need to be trained in how to properly secure their tools, what types of tools are prohibited, and what to do if they see a foreign material intrusion event. Exclusion is the name of the program, but intrusion would be when the bad thing happens.
If something happened, we'd be okay, but what I want to make sure is that you understand the rules and regulations associated with going over the core, and as far as form material goes, we don't want to drop something.
So I don't drop something. I'm taking training so I don't drop like camera pieces or anything in the core.
That's right.
So I guess the point is I'm not just going over an open nuclear reactor. This is a coordinate.
There are certain components like tie wraps, at least at the plant I worked at, that were straight up forbidden in the reactor containment building.
And we're going to have to like be careful about how I hold things, right?
Yeah, absolutely.
Okay, cool. Thank you.
Yep.
Okay, time to dress out.
I don't feel naked, but I feel less clothed.
They actually refer to those, I've heard those scrubs actually referred to as modesty garments. And they're also what's given out if you become contaminated and you have to say, lose your pants.
Well, you are.
Okay, cool. So where are we going exactly? We're going over the fuel?
Yeah, we're going to go on the refuel floor bridge. So
what is this? Can we look at this?
Yeah, actually, that's a really good picture right there. So what they're doing is, this is a picture of our core uncovered right here. And
that's where we're going?
Yeah, there's a bridge that's sitting over there, and there's almost near about 100 feet of water that's over all that fuel, and we're going to ride.
So quite a few assemblies still in there. I don't know if they're offloading and they're just starting, or if they're reloading and they're almost done.
A bridge, a crane, essentially, that goes over there and moves the fuel.
Is that what is happening here? Like I'm seeing a camera. Is this on the crane that's moving?
Yeah, that's on the mast on the crane. That's all the way down. Right now, there's another portion that you're not seeing the spent fuel. That's where they're at right now. But there's a mast that goes all the way down into the core, and it'll latch onto the fuel, and we'll move the fuel.
So this
highly specialized profession, highly specialized individuals that operate that crane. And at least at the plant that I worked at, you are required to have someone, a licensed senior reactor operator, be on the refueling bridge during a refueling operation, what's known as the core load supervisor. That job, let's just say it wasn't for me. Basically, the main reason why I didn't care for it was because you would have to be on that refueling bridge for upwards of 4 hours straight sometimes. And I can't hold it that long. But yeah, and there isn't exactly a place to go while you're there, because you're in a radiological controlled area. No eating, no drinking, and no going to the bathroom. That's the bigger hazard that's up there, at least to me. Forget the radiation part.
Blue that I'm seeing, is that Cherenkov radiation, or is that lighting?
Well, that's probably lighting over there. You'll see some Cherenkov when we moved.
Wait, you're going to want to wait and see it up close.
The bundle here, you'll probably see it, but there is a blue glow that'll be around the fuel itself.
So is this a crane operator, like actually grabbing things?
That's right. You'll see it when we go over the next bundle,
dripper.
but there's like an open claw, and then the camera is an
All this is a submarine crane, which is cool.
open claw, and then it'll sit down on the bundle, and it'll latch onto the bundle.
Really? Okay, cool. And and all these are different fuel. Man, it's crazy. So it's just like the claw game almost. They're just kind of putting things in the little slots.
Yeah, they've all got specific places.
A little easier than the claw game. You really don't want to drop a fuel assembly. But there's all sorts of interlocks, mechanical interlocks within the crane mechanism to prevent you from doing that, and also to prevent you from latching on if you got, say, a bad angle or something like that, all to prevent dropping a fuel assembly.
Supposed to go. We keep very close track of where everything's at, and there's a lot of, I guess I'll say poisons, especially in the spent fuel pool, where we make sure that we can put the fuel and the fuel stays subcritical at all times.
Oh, so that.
All right, so he's talking about like putting in boric acid to ensure that you have adequate shutdown margin. Subcriticality is another word for that. Basically, you are so far below starting a nuclear reaction by that much in terms of reactivity units. Basically, to make sure you're shut down by way more than the minimum requirement to remain shut down. And of course, as you're moving fuel out, your shutdown margin is going to go up because you have less fuel that you could possibly have to take a reactor critical.
So this is the reactor?
This is the reactor.
And then this is the spent fuel pool.
Well, the crane's going over to the reactor at this point in time. It was in the spent fuel pool, so now you'll see it come over the reactor here.
Whoa, that was a cool reveal. That was pretty neat. So this is what the reactor looks like.
Yep.
Okay, so I guess this is a question I have. So we've got cameras.
And this is typically what you see. Everybody has these cameras logged in on something because everyone is tracking the refueling part of the refueling outage in every department because there's certain things that you get handoffs for so you can do certain jobs. Once the core is fully defueled or fully refueled, various things you need to do in other parts of the plant. So everybody at the plant is watching this.
And Philip, you were saying don't use like non-cotton fabrics. You're saying that's bad, right?
Not necessarily bad. Synthetic fibers tend to have more static electricity. And
static safety, sure.
Static is what radon gets, it will adhere to it.
So when the radon attaches to it, I'm not going to be able to get this out because the RP won't let me.
Yes, so something that really has nothing to do with the reactor itself, but it can affect the sensitivity of the instruments. And some of them have radon rejection, like I've noticed sometimes when you walk through those portals that scan you, it'll say, hey, you're clean thanks to radon rejection or something like that. But even that's not 100% foolproof, so you want to try to avoid radon. And really, worst thing that'll happen is they would take your clothes, they would examine them, make sure it's not contaminated with everything else, and then give them back to you. I even remember when I first started working at the nuclear plant, my first day at there, I didn't into the radiological controlled area. Yeah, they took my pants and I had to wear some modesty clothes for a couple hours until they gave them back to me.
It'll set off the radiation detectors, and then you can, most of the time, you can just let it sit for a little while and it will decay and you can get it out. It might be the next day, but
that radon is all naturally occurring. That's
not from the plant.
That's not us.
So the RP personnel.
That shows you how conservative we are at the nuclear plant, is we will pants you if you get a little bit too much background radiation due to static cling.
I learned about in the safety training, the people that have to scan you so that you can come out, they have to make sure that you're clean. And so a lot of times radon is the stuff that gets on your bag and that'll set off their detectors and you can't get out.
Yep.
Right.
Okay. So
and same thing with your clothes. If you wear synthetic fibers, polyester or nylon, stuff like that.
That was what got me. I wore polyester. That was my amateur nuclear noob moment of my career.
Same thing.
Got it.
You're about to pull a fuel bundle out of the core, and I think you'll actually see this rank off effect here when it comes out.
Really?
All right, so we're defueling. Okay, so the outage just started. That actually makes sense for the timing of this video, because refueling, trying to time that right, or I guess reloading the core, I should say, is going to be challenging if anything changes with the outage schedule, but going and having him be here during core offload makes more sense, because that date's a lot more predictable.
He's trying to grab it first?
Yep. What they're doing is they're on the bundle, and they've each got unique identifiers, serial numbers. You can kind of see it right here. So they're going to verify that they're on the right bundle, and then he's sitting on it, and then he'll latch onto it, and then he'll make sure that he's got a good hold of it, and then he'll bring it up.
This person has a peer checker and an independent verifier to make sure they're on the right spot, and the SRO supervisory oversight, and a reactor engineer following and measuring counts during each of these operations to make sure you don't get any sort of flow or radiation anomalies. One of the most supervised jobs there is.
Used to do, isn't it?
I did this for a little while, yeah.
You were, what do you call this person?
I was the reactivity manager over the fuel handler.
Fuel handler, okay, cool. So he's securing?
Yep.
And is there some video we can get of this?
Absolutely.
Are they recording this?
They are.
And so now he's flying the bundle. Or she, whoever it is.
Withdrawing it.
There's just a rank off effect right there.
Oh, yeah. So how far above the pool will we be?
See it really well in the hole right there that was just vacated. So we're about to head to the plant. We're going to swing by RP. They're going to give us a RWP, a radiation worker permit. We're going to sign in to go into the plant. We're going to understand our dose limits and all that type of stuff. Then when we get up, I'll take you up to the floor. And then when we get up to the floor, you and I are going to change the jobs that we're doing because we're going to go out on the bridge. So you and I will have another RWP we'll log on to.
About foreign material dropping into the pool.
Yes.
And so I'm hyper aware of
There is you are absolutely required to take training on that if you're going to be going in any of these FMEA, so that's for material exclusion area. And this is going to be the FMEA 1, which is going to have the highest level of controls, which makes sense. I mean, after all, you're over the refueling cavity. Sometimes at various stages of the turbine outage, that can also be labeled an FMEA 1, but someone's going to log everything you take in with you. The FME monitor will log everything you have.
Right now.
It's one thing we do. I mean, it's taken weeks to get you in here, and the only thing we've done is really just train you for a week pretty much before we got.
And that is the nuclear industry in a nutshell. Train you for weeks, provide a bunch of briefings from each independent group. So your job brief, your radiological work brief, your FME brief, your plant status control, which is about bump hazards, and making sure you're manipulating the correct component, and all those briefings and organizing times can take a couple hours, and then the job takes maybe less than one. Yeah.
Right.
Yeah, absolutely.
We want to make sure you're prepared.
Yes and yes.
How are you, buddy?
The login area.
That's an interesting fellow right there.
Yeah?
He's our valve guy.
A valve guy?
Yep.
You have a whole guy just for valves?
Yeah, we have a couple.
Probably have a whole department just for valves, a whole subset of mechanics that just work on valves. There's a lot of valves.
Guys just for valves, but he's our lead guy for valves.
There we go, lead valve guy.
We've only got one right now. I'm like, well, that's a little different than tank.
Yeah. Can I see your tattoo real quick?
Yeah.
That's awesome. That's cool. Thanks. Pretty good.
Guys.
I think this is RP?
This is RP, yeah. This is our briefing station before we head out into the plant to make sure we understand what RWPs we're getting off.
That's good.
So when you go to log in, it's going to ask you to scan the front of your dosimeter first, scan that barcode. Yep. And you're going to scan, it's going to say scan the back, it'll be that barcode. It's going to ask you for a work order number. Type this number right here at 125-129-292. Then it's going to give you a drop down box. You hit the little arrow, and that's going to be the only number that's available. It ends in that 121. Okay?
Yes,
that's
sir.
going to be y'all's RWP. It's going to get y'all up to the refuel floor, traveling through Unit 1. Be able to take y'all in the office. You can check in up there. Now, when you get up there, make sure you let them know your set points for your RWP. It's 5 millirem dose alarm and 40 millirem per hour dose rate alarm. That's fairly low to be going on the refuel floor. So that would determine where they're going to allow you to go, or if they want y'all to be on a different RWP with higher set points. Okay.
That's a good point. Confirming where the alarms is, because just because your dosimeter goes into alarm, that doesn't mean, oh my goodness, something scary and horrible happens. That just means you exceeded what you briefed for. And radiation protections would come in and get you, would evaluate, make sure you're okay, and the radiological conditions can change a little bit depending on where you're at in the outage. So that's also an interesting point. The other thing is, and this is a little different compared to where I worked, they mentioned walking past Unit 1. At the plant I worked at, they were separate. So separate reactor containment buildings. And they were probably a good 300, 400 meters away from each other as far as where you'd even go. And there'd even be a bunch of signs that would say plant status control area, this is the operating unit. That is to say, don't go take stuff apart in this unit as one final little catch-all, even though you're briefed a zillion times and they're physically separated from each other. So this introduces a bit of potential risk of walking by equipment that you don't necessarily need to walk by. So it's definitely one of the trade-offs of keeping your units right next to each other.
5 and 40? 5 and 40. Okay. Just make sure that the technicians that you talk to up there know that.
Yep, I will.
All right.
Let's get you one of these.
So we can grab any of them.
Well, we want a smaller one. We don't want a screamer.
Screamer, the ones that track your location.
A screamer meaning a loud one?
Yeah, so if you're in like a high noise area.
Oh, okay. A loud one. Okay, I've actually heard it referred to. There are some that track your location, but those are only on certain higher radiation areas. Different people call things different things, I suppose.
So we're going to go to a white trip ticket area. Anyone that says white is fine. Put your dosimeter in there first.
Yellow for high radiation area.
There you go. Yep. Yep. And then it's going to ask you to scan the back. Now this is where you pull up your view your RWP. So click view RWP. This is what we talked about earlier in the training, right?
Mm-hmm. So every worker does this.
You are granted access to the RCA.
That's a pretty big deal.
And then you're going to put that right next to your DLR.
Sounds great. Here we go, about to go in. So you've been saying for years you didn't ever think this would happen? No, I really didn't think Bill would pull this off. So we're actually about to do it.
I am just as surprised as AR that a site would be willing to spend this much resources to do this. This is fascinating.
It's a pretty big deal. Bill, are you proud that you pulled it off?
Let's not give me all the credit, because if this goes awry, I don't want to be the one that goes down, man.
It would have taken a lot of sign-offs from a lot of different departments.
But it's a pretty big deal to be able to take a camera into a place like this.
It is a huge deal, yeah.
That's what I'm talking about, baby. Get in there.
It's exciting. Is that Kevin?
Yeah.
All right, so here's what we're going to do. We're going to go in the RCA. You're going to put your dad on here. Philip will go in last. Just make sure you're all good. You get the green light?
Yes.
Go in.
Put them in right there.
Now you got your...
These turnstiles are the exact same way at the plant that I worked at.
Hard hat?
Yes,
safety
sir.
glasses?
Yes,
hearing
sir.
protection? DLR? And your dad, right?
Yes, sir.
Good to go.
Great. Currently, I have 0 milliram.
That's good. That's
So we're going to an industrial environment so it can get a little loud, okay?
Yes, sir.
All right,
Hearing
y'all ready?
protection.
Let's go.
They're showing all this traversing through the RCA. Wow.
So we're in the RCA now.
We are actively in the RCA, that's correct.
It's very...
So all of the primary support systems that are going to be located near the reactor are in the RCA. This is in contrast to, say, the turbine support systems. Though that being said, especially in a boiling water reactor, things can turn into RCAs if conditions become prevalent that there's, say, elevated dose in the area for some reason. There's a lot more radiation monitors in the secondary part of the plant for a boiling water reactor than they are within a pressurized water reactor. Though there's still a fair bit in a pressurized water reactor. We had quite a few in the plant that I worked at as far as radiation monitors in the non-nuclear part of the plant. Now, in this part, there's radiation monitors everywhere, which is good.
It is.
Video.
That low-dose waiting area is a place that has been surveyed and been determined to be low, so you're not sitting in an area if you're just waiting and picking up dose unnecessarily.
Okay, so what I'm about to take you into is the secondary containment area, right? You'll notice that there's some locked doors and everything, like watertight doors. We do this intentionally because this is our absolute last means if something bad happened. That's where we keep it all. We keep this area at a negative pressure just to make sure we keep all the containment products inside secondary containment if something were to have happened.
In contrast, the control room is kept at a positive pressure to prevent anything from going into it. So this is the opposite.
So that's why you see the doors like
So that's an air and a water door.
a flow tight. Yeah, it's not really an air door. It's mostly a water door.
Okay.
Watertight.
Yeah, that's going to be watertight. In airtight, you would go through something called like a personnel airlock type door, which is what the primary access to the main reactor containment building at the plant that I worked at.
Do we have to badge in to go?
Yeah, we're going to have to badge in. So I'm first in.
Yep.
And we're going to walk up to the elevator through the operating spaces because there's less traffic over this.
And before we go any farther, when you see the floor drains, don't step on those. 'Cause they're a lot of times contaminated.
Yeah, they're usually marked with radiological symbols on them and coded so you see right where they're at.
So be looking for floor drains.
Like that one right there. And another one.
So we have 185 control rods. There's 185 of these accumulators, which will assist the control rod to enter the vessel in the event of a scream.
Got it.
Yes, because gravity is not helping you since you're going from the bottom up, compared to the pressurized water reactor, which doesn't need these. You just fall in.
So they're individual pressure tanks with check valves to maintain pressure.
Effectively, yes.
Okay.
Well said.
So it's contaminated just because water has gone down into it.
At some point in time, the surface is most likely not from where we're at, but inside those drains,
It's conservative.
there may be some contamination.
I see.
We don't know, and getting into the drains and pre-releasing it is very difficult, so we just say, stay out of it.
Don't touch it. Got it. I'm getting no dose.
That's a good thing.
We're gonna go up
Though I
to-
appreciate him doing it for the camera, because a lot of people, there's a lot of misconceptions out there that think, oh, you get all kinds of dose at the nuclear power plant. I never got much throughout my career. Of course, engineer, control room operator, supervisor, and then manager, you typically wouldn't as much, but still, a lot of people think you get a lot of dose.
fourth elevation, we'll pick up our C-zone clothes that I suspect they're gonna ask us for, and then we'll head up to refill floor.
Okay. What RP you on? Or what, how do you say, RWP?
RWP.
What RP you on would be what radiation protection are you on?
5200022.
Is that how I would say that to you? What RWP you on?
Yeah, that's typically how it goes.
It's more like how long till lunch? That's what we normally talk about?
Yeah, something like that.
This is a big motor.
Yeah, they're abandoned in place at this point in time. That's how we used to control the speed of the recirc pumps before we had static control. So we've moved over to the
Yeah, you'll see some big things abandoned in place because the engineering cost could be too much to effectively remove it because of all the lineups associated with this component.
drives, but these are some big old motor generator systems.
It's easier just to leave them there.
Yep.
Yes.
Abandoned
in place, usually associated with the phrase, the engineering costs would be staggering.
in place. Interesting. So we're going to dress out here?
No, we'll take our stuff up to the refill floor and get briefed up there, but we're going to grab our booties and everything
I was
here.
going to say, you wouldn't want to dress in a really confined... I mean, this doesn't meet the definition of confined space, but it doesn't exactly look like the best spot to play dress up.
Okay. Are you getting one for each of us?
I can, yeah.
Can you hold it? Oh.
I'm scared to touch anything.
Good. Stay that way.
Stay that way?
No.
Yes, that is, well, scared. Don't be scared, but be hesitant to touch anything. And that's good plant status control behavior. It's called having reverence for the plant and treating every component with the respect that it deserves because, hey, everything you see here maintains this awesome thing that is a nuclear power plant.
I have no clear plastic. Do you have any clear
I
plastic?
have no clear plastic.
Thank you.
Thank you.
And that is an example of an FME control. No clear plastic beyond this point, because that stuff is difficult to spot. Yeah, again, so many signs.
Your license? Your license?
How y'all doing? Good. So you're the RP?
Yes, sir.
If there's one thing I learned in that training, is to say Mother May I to you before I do anything.
Oh, really?
Well said.
FME is gonna love these guys.
Yeah.
Yes.
We've been briefing them up. This will be my test for them.
What do you think they're going to do to me?
You're gonna get the rigger trying to get all that stuff out of the bridge.
You think so?
Yeah, all the FME tie-offs for all this camera equipment.
Yeah.
He's got 2 cameras. Good luck.
A lot of straps.
A lot of straps. Yeah. What's your name?
Trenton.
Trenton, I'm Destin. Nice to meet you.
Destin.
Oh, I didn't like that handshake. Let's do it again. That's a better one. How long you been here? In terms of...
I like how wholesome a lot of this is, and that really, it does come down to a lot of interactions in the nuclear plant.
Yeah, nuclear.
2011.
Really?
Are y'all going out too?
Just me and Destin will be. Yeah, we're gonna take the other guys up to the crow's nest.
Yeah.
And Destin and I will be out on the bridge.
So you're RP?
Let me get your ID. Let me get your ID.
18504.
Always be nice to people on the elevator. They might be your RP later.
Now I've got to ask you what your RWP is.
My RWP is...
Don't start stuttering now.
121? Is that it?
Here we go. You get the sheet.
That's my work order. It's...
Yeah, I was gonna say, you don't have to memorize it, just keep it written down, but yeah, you gotta know what your RWP is.
125, 129, 292.
That's your work order. You're right. Your RWP is 121.
Yeah, 121's my work order.
Your RWP.
RWP. Dadgummit.
What's your ID number on that?
My ID number is 37467.
So you'll be on 25, like I said, you'll be on 25 20092. The dose alarm is 60 milliram.
Okay.
The dose rate alarm is 250 milliram per hour.
Alright, this is what our RWP looks like. When you go to look at it, got your description. This is for refuel floor activities. It's for high radiological risk, so this will gain you entry into high radiation areas, even though we don't have...
That makes more sense, putting you on that type of RWP for getting on the refueling bridge.
One post where y'all will be at, but just in case, moving things throughout the water, high radiological risk is a possibility, which is why your dose alarm will be the 60 milliram. So in the area where you'll be at on the bridge. So if you look over there to the
orange
top
part?
right panel, yes. You look at this top right panel here.
Those are going to be the FMEA boundaries, those orange bits, and they usually have something that says such on the actual barrier.
Bridge. This is the bridge. You see all these people on here?
Yes, sir.
So that's where y'all will be at.
Yes, sir.
So the dose rates up there are about 1 to 2 milliram an hour. So that's where we come to our dose rate alarm. Your dose rate alarm is set to 250 milliram an hour.
That's a good
On
bit
the
of
bridge,
dose.
you shouldn't get close to that at all.
Because of the water.
It's the water. Water's your shield.
If you're setting off that alarm, then something crazy just happened that would probably indicate either your EPD's broke or you might need to start getting people out of there.
It's your mediator. We have stop work criteria. In the event of a dose alarm or unanticipated dose rate alarm, will notify RP.
That's a microphone.
Oh.
I was just having a hard time hearing you.
Oh, there we go. Yeah, stop work criteria. In the event of a dose or a dose rate alarm, immediately notify RP. Stop work, we'll leave the area. We have air monitors on the north side. So if you hear those go off, and you'll hear them go off, that means everyone in the C zone or on the floor will evacuate, and we'll help that transition, and we'll leave the floor entirely.
Will RP be on the bridge?
We will have RP in the zone, and they will be covering the bridge. We have telemetry,
Detectors
so we
on a
can
stick.
constantly monitor the dose rates in the area. So right here, you see these little dose rates.
Yes, sir.
So that's for inside the 360 platform, and that's for on the bridge. So if you look back to our screen over here, you'll notice on the left camera, there's a 360 platform here. So we have RDS 31s monitoring the dose where the workers are actively working in the 360. So this just helps us see the progression of dose rates in the area from afar. That way we can let anyone know, what's going on.
So you've got instrumentation right there, and we're going to be on the bridge right there where they are, correct?
Correct.
And then, so you're monitoring it in real time, and because the RWP is active, you know that we're out there.
That's correct.
Okay.
Yeah,
Okay.
so everyone's covered all the way around, both ways and backwards.
Sounds good. And so I'm at 0.1 millirem an hour, which is nothing.
Right, and now you're about to sign off out here and sign on to, because you probably come up on what, 71?
It came up on 121.
121. So we're going to sign on to 252.000.92.
Yes, sir. And then my rate alarm will go up.
Right, so your set points will change. You'll go to a dose alarm of 60 millirem and a dose rate alarm of 200.
So essentially what we have here is concentric radiological work zones. So he had the lower dose one that he was able to make it to here, but since he's going to go on the bridge, he needs to have one with higher set points so you don't needlessly set off alarms. And so he's the sort of person that his job, his work permit is set for the appropriate level for the hazards that are in the area.
50 millirem an hour.
Cool. Thank you. I appreciate it. What was your name?
Christian.
Nice to meet you, Christian.
Nice to meet you.
Yeah.
All right, now that you stop back by this window, you got a full brief on it. We do a reverse briefing.
Yes, sir.
Nice.
The dose alarm and dose rate alarm, we typically what we do is say, hey, what's your dose alarm? You repeat back to me what the dose.
A reverse brief would be you briefing the RP guys, and we've done this in the control room with pre-job briefs. For a task that is done almost entirely in the field, the plant operator or the maintenance technician would come to the control room and tell them what they're going to do, what the operational impact is, what their mitigating actions are, what their backout criteria is, and basically everything you need to know from your perspective in the control room to ensure this job is conducted safely.
Which would be 250. And then I ask you, what's your dose rate alarm?
60.
And you say 250.
It's 250 millirem per hour?
250 millirem per hour. Yes, that's correct.
What's my limit dose? Is it 60? It was 60, so I said that backwards. Okay.
Yes.
So the dose rate alarm is 250, and the dose limit is 60. Yes, sir. Millirem.
One's a millirem and one's a millirem per hour.
Yep.
Yes, sir.
So the dress out is going to be a full dress out with the single dress out with the hood.
So single dress out, and that's really for protection against contamination rather than radiation. There are some jobs that are pretty dirty that you actually wear double the number of protective clothing. So that's what he means when he says single dress out, not doubles.
On the bridge, and that's to protect you because you're going to go into a contaminated area. Contamination levels in the area on the bridge is less than 1,000 dpm per centimeter squared, up to 2,000 dpm per centimeter squared. So low level contamination, minimal dress out would be. We have several different dress outs, so this would be the minimal dress out.
So we're not going to be quite to the level he is, or is it going to be the level he is?
It's the same dress out as
You want a hood, not a skull?
Yeah, that's level 1, if you will. There are some jobs that I've seen where you essentially could just wear a lab coat for very light amounts of contamination, but most things you see today that involve going in the reactor containment building, you're going to need the full set of PCs, and that's considered the low level of dress out.
Yes. Okay. We'll have to go get a hood.
Okay.
Appreciate it, guys.
Okay. So my max is 60, my rate is 250. It's a single, and then you do want to send hood and skull cap.
Right. And then it gets a little tougher, 80% of 60.
80% of 60 is 40. Hold on. It's 60 minus 12, which is 48.
48, yeah.
There's a lot of math under pressure here.
48 is when I need to start looking for the door.
Right.
Okay.
So that'll be the time you have to evacuate.
Sure.
So other than that, Christian briefed you on the dose rates on the bridge, and now you have the information for the contamination levels on the bridge. You did a reverse briefing. Is there any questions or concerns?
I have a question for you guys. What do you guys think I'm going to get dose-wise while I'm in there?
You're around about 0.5 milligram per hour.
0.5? What do you think my total is going to be? It's going to be based on time.
It's going to be 0.5 milligram per hour, and you'll be in there an hour.
Okay.
Yeah.
Okay. Cool. Thank
That's
you.
how long it takes you
Appreciate
to get in and out.
You're welcome.
You're not going to be in there an hour.
Not going to be in there now? It's Mr. Summers, right?
Yes, sir.
Yeah, thank you, Mr. Summers. Appreciate it. Thanks, Christian. What was your name?
Jonah.
Jonah? Nice to meet you guys.
All right.
Sorry.
I like that they included the pre-job brief as part of this. That's really shows you what the sort of things you see in the nuclear industry.
Hey, what's up? We're on the refuel floor now?
We're on the refuel floor.
Okay.
We can go ahead and take you up to the crow's nest. It's probably the best place to be.
What all you carrying in?
Are you going into foreign material?
Yes, that's what I was trying to figure out.
Yes. Foreign material exclusion with all the camera stuff.
How to
go about it.
Would you like this on my head?
I met Jeffrey from FME, or Foreign Materials Exclusion.
Yes.
I didn't really understand what he was doing at the time, but he was starting a process that was happening in the background. He looked at all the cameras that I wanted to take out over the reactor, and he started working a solution for how to attach them to me.
When we come up here.
Yeah, you really don't want to drop those cameras into the refueling cavity. There was one incident during a refueling outage where the residual heat removal pump, so the pump that keeps the reactor decay heat removed, sucked in a face shield that was inadvertently dropped into the refueling cavity, and then the pump proceeded to tear itself apart. Didn't result in any radiological accident or damage to the core or anything like that, but it did extend the refueling outage by quite a bit because they had to get that pump fixed. These foreign material exclusion, or FME events, can get quite expensive.
We're in a really interesting place, but everybody's all business.
Yep, nuclear professionals.
All right, so this is our refuel floor. You got 3 units up here. You can see all 3 units spent fuel pools. You can see all their bridges and everything like that. We're currently in refueling operations on unit 2 right now. They're right over the fuel pool, and they're moving either blade guides or fuel over to the reactor at this point in time. They're actually in the process of shuffling their fuel.
Okay, so I didn't realize when I heard nuclear fuel unit 1, 2, 3, or nuclear reactor units 1, 2, 3, I didn't realize it was all under one roof.
Oh yeah.
I didn't know.
That isn't necessarily a common thing. Or let me rephrase that. That isn't a universal thing. Units 1 and 2 were very different at the plant that I worked at, and they were physically separated in completely different buildings.
Yeah. Yeah,
So,
it's a big building.
So that's a reactor.
That's right.
That's a fuel pool.
That's right.
That's a fuel pool.
That's right.
That's a reactor. And then what do I have going the other way? Oh, square
Fuel pool
first.
and a reactor.
Fuel pool,
Unit
reactor.
2 and 3
Just
look
like
identical
that.
to each other.
Why are these fuel pools next to each other?
So they were made.
So that's why they call it secondary containment here, because the actual ones are around each individual reactor vessel, which of course in the outage unit is completely disassembled so they can refuel.
Originally when it was constructed, they just constructed unit 1 and 2 as mirror objects of each other, and then at some point in time during initial construction they said we want to add a 3rd unit to it, and then just mirrored unit 2 again. So it's just from an original design.
I see. Interesting. And this was made when?
Back in the mid-60s.
Mid-60s. That's amazing. I can see into the pool. I can see the
A lot of these plants are pretty old. Their initial license lasts 40 years, but you can get 20-year extensions. And it's not unheard of to even get a second or potentially a third 20-year extension.
Tops of, I need to flip my camera to a tighter camera, I think. Let me do that. So there's a nuclear reactor around that ring. It's in the center of that. That's
right.
Unit 1?
That's Unit 1, correct.
Here's the fuel pool for Unit 2. Now, is this spent fuel or?
Yeah, the square is the spent fuel, that's correct.
Okay.
The spent fuel pools and the refueling pool being in the same structure. That's also not a universal thing. At the plant I worked at, they were separate buildings, and it even went through what's called the fuel transfer tube. Basically, stuck it under, there was an upender, which slid it and bent the fuel assembly back, slid it through the tube, and then took it back up, and then it was placed in the spent fuel pool harness. It kind of looked like a little strainer or grater or something.
And then the reactor's right there. Right now, are we taking fuel out of the reactor or are we putting it in?
So it's a little bit combination of both. We actually
Interesting.
We have 764 bundles in the core, right? And we only get about 350 new bundles every refueling average every couple years. So we actually reuse the fuel for about 6 years. So they call it a shuffle. You may be moving a once burnt fuel is what we call it, one cycle, moving it to a different location in the core.
Okay, yeah, that's normal. Yeah, at the plant I worked at, only about a third of them were freshly new, and that you would have some once burn as well as some twice burn before you'd put them in the spent fuel pool.
Right now, the main priority for Fuel Shuffle 1 is to move the fuel in an appropriate location so that we can access the parts of the core that we want to do maintenance on.
That makes sense. Can you walk me through? I see a lot of people in this room. I see a lot of people doing different things.
Mm-hmm.
This looks like there's a lot of equipment over here that's not being used at the moment.
Yep.
Is this a monitoring station?
Yep.
Okay, so it's monitoring radiation. So I don't see any people here. I see these people here. They look like they're getting ready.
You generally don't want people near the operating unit during an outage.
Yeah, so you got a bunch of groups that are working here. You've got some, I'll say, work management individuals down here.
That's
from
what these people
groups.
are doing?
These guys are helping track the fuel moves that they're on, making sure that they're on the right bundles, etc. They're also tracking the work that's going on the refuel floor, reporting to our outage control center.
That's why people are coming in and signing in with her.
That's right. They're just tracking the work of what's going on. That's really what they're doing.
Okay.
You got a bunch of Boilermakers out there that their job is to essentially remove.
That's a little interesting. You have your work management people actually inside the reactor containment building. I think that's got to be the function of having it be 3 under 1 roof sort of thing, because I've seen it essentially at a smaller building outside where people sign in and get work started.
Disassemble the vessel.
Is that who you're seeing here?
There's a couple Boilermakers down there. There's a bunch of miscellaneous stuff. If anything that requires any crane movement or anything like that outside of the bridge, you got Boilermakers involved. You got foreign material.
And after all, the reactor vessel is just a really big boiler.
Individuals out there that are tracking what foreign material is going where.
Mm-hmm.
Okay, and then up on the bridge, they're over the reactor now. I'm seeing some people right at the edge of the reactor.
Yeah, those guys are actually part of our in-vessel inspection team. And what they do is they go and they have cameras that they put in the core, look at our nozzles, look at our welds, look at our all that stuff to make sure that there's no wear essentially, and that the life of the core is maintained.
Got it. And that's an individual on the bridge right there. Is that the individual getting the fuel rods?
That would be the fuel handler himself, yes.
Okay. And then there's support people beside the fuel handler.
So you've always got a fuel handler. He's got a peer check that's with him, and then you have a licensed senior reactor operator to authorize the fuel moves that are occurring.
Wow. So is there like a physicist somewhere? Like, is there like a really smart nuclear physicist around the room somewhere?
Well, there are nukes that are watching all this, but they're in another
That's what
room.
they're called, nukes?
Yeah, we call them nukes.
Okay.
Referred to people as nukes that were just in the Navy, and I think a lot of these guys were people that were in the Navy and later joined the civilian workforce. I'm not one of those people. I don't have any naval experience. More than half of my coworkers did. Though the term of physicist, as far as like a reactor engineer or a nuclear engineer. The term physicist isn't really used because, I mean, there's not any like pure scientists per se. There's a term, health physicist, which is a more of an analyst type role for radiation protection, but you typically don't see scientists at a nuclear power plant. I mean, it's heavy industry, power generation. You don't really have like experiments or anything like that going on where you would have a physicist or any other forms of pure scientists.
Engineers, and they're in another room outside of here. They just limit their dose that they're receiving, right? So,
I see.
So they're
yeah, when I was in the engineering department, I didn't really get out into the plant as much. It just wasn't part of that job description compared to, say, being in the operations department.
To them later, but they're in another room over there and they're watching all of this, and they have worked with our corporate fuels guys to figure out what the appropriate way to shuffle the core is.
Gotcha. Okay. And so these people over here, if you'll look at my camera screen, those people just went into the C zone. You call it the C zone. That means contaminated?
Yeah, contamination zone, that's correct.
Okay, so somebody's coming out. So he's about to come down and derobe. What do you call the act of taking off your... Someone handed him something.
Yeah, well, we had to get something into the C zone area, so he passes what's in. And once it goes in, it's okay, but they can't take it back out.
Yep.
Okay, I noticed the bridge just moved.
Got to be evaluated and deconned.
And what is happening now? So he's at the reactor itself.
Yeah, it looks like he's going down to get a fuel bundle at this point in time in the core. He probably has one latched on. He's coming right now through the cattle chute.
Oh, he can go straight through.
Yep.
You call that the cattle chute?
Yeah, it's just like, it's just a generic term that we utilize.
Gate?
It's a gate that we can come through. And
those gates, all right, so this was a lot simpler than the plant that I worked at, that it's just this one little canal that connects the spent fuel pool and the reactor cavity, because you would have to go through another canal, then transfer through the fuel transfer tube, just because it was in two separate buildings. But in a way, this looks a lot nicer, actually. But again, the trade-off is having 3 units right next to each other. You're just going to have that much more robust of a design for your containment structure.
He'll have the fuel at the end of that crane, and then he'll put it in the appropriate location in the spent fuel pool.
So what is the coordinate system for where the fuel is located?
There's a map down here I'm happy to show you.
Yeah, I'd love to see that.
It's like playing a game of Scrabble.
Second.
Yeah.
I want to watch what he does here real quick.
So they'll get over the location that they want to go, either in the core or the spent fuel pool. The bridge will automate to where it's supposed to be at, and then he'll call out the core location or the spent fuel pool location that they're at, and then his peer check will agree with them. They'll lower it, and before they latch or unlatch, the SRO will give their authorization that it's appropriate.
I actually see the hole he's about to... Do they light up the holes where they're going?
There's some lighting down there so they can see where they're working.
I can see what he's trying to align to.
Depending on where they are in the refueling portion, they'll sometimes adjust the lighting just so it'll be easier to see.
Here's one of our refueling SROs leaving right now.
Should we talk to him?
Sure.
Sure.
Hey, Sarah.
I just backed down that ladder because I saw you back down the ladder.
So, do you know why he did that?
No, why?
So, this sign right here says, hey, this is a ship's ladder. The incline isn't appropriate for you to walk up it normally, so you've got to maintain 3 points of contact.
Yes, that's...
So, he should have seen that you had all this equipment on you, and he should have said, hey, Austin. Did you say Austin?
Destin.
Destin, I'm so sorry. You should have said, hey, Destin, make sure you secure your equipment and maintain 3 points for safety.
So I'm kind of, what's your name?
I am Sarah.
I'm Destin.
Nice to meet you.
Sarah, I'm kind of torn right now because I want to appreciate you for doing that, but also I can tell that you're kind of talking smack to Bill.
No,
coaching's coaching. That's how we take it.
It's coaching.
Okay. No, it's up and
Feedback's a gift, a non-refundable one at that.
like 100%. This is normal.
Got it.
And is this your first time at a nuclear power plant?
Yes, ma'am. One second, I'll turn this on. Sarah, what's your role at the plant here?
I'm a senior nuclear reactor operator, and I'm a fuel handling supervisor. I just came off of Unit 2's refuel bridge, and we're in the process of refueling Unit 2. We're in the process of 202 fuel moves in fuel shuffle number 1. I'm providing direct oversight of the fuel handlers. So there's 2 people here.
Ask her how long she had to stay up there. That's the real question. Gonna be something like 4 hours.
Where the mast is, and then there's
Before taking a break. I mean, obviously you work 12s, but
Allison, who's got the red gloves. She's my counterpart. She's just taken shift. So she's the fuel handling supervisor providing oversight of the fuel handling, the fuel movers.
So she's in charge.
That's right. They're operating underneath her license in her direction.
So she's...
Yep, so if they screw up, it's all her fault, because she's the one with the SRO license.
Reactor operator.
She is a senior nuclear reactor operator, that's right.
Forgive me, what's the difference in just a normal reactor operator and a senior?
Different license.
You have a technical specification responsibility that you maintain that the plant is operating within its license.
So
the senior reactor operator is the supervisor or management role, and you actually manage the reactor operators that operate in the control room. Now, what she's doing is different, that she's over a team of contractors that are doing the refueling operations, but that can only be done by senior reactor operators. A reactor operator license isn't enough, and getting the license has its own set of requirements, and it's typically harder, because it requires everything that a reactor operator is required to do and then some. So it's just adding in the technical specifications, like she said, plus the necessary management and leadership skills that you would need for that particular position. And it is possible to get a senior reactor operator license without having been a reactor operator. I never had a reactor operator license. I went straight for senior reactor operator, and that's based on my education and engineering background. I was considered to be eligible to do that. Well, to essentially skip that step, it's what's known as a instant SRO or direct SRO, depending on who you talk to. There is also a specific type of SRO license that's limited to this refueling operations. I've known a handful of people that have had that, but it's less common.
So Sarah, you had to train to be a reactor operator.
That's right.
What's your background?
I went to Mississippi State. I was a biology chemistry major, and I joined the National Guard. I deployed to Iraq. I came back, and my husband had come to Huntsville, so I transferred all my hours to UAH. I finished up my degree there.
In what?
In biology and chemistry. They were not hiring in Huntsville, so I decided to work on my PhD in biotechnology. And finally, TVA came for a job fair, and they were not looking for engineers. They were looking for biology, chemistry majors, and so
interesting.
I'm here at TVA as a chemtech, and
a PhD for chemtech. That's interesting. Most people I've known that have PhDs, like, you don't see a lot of PhDs hired at a nuclear power plant. And mainly, I think part of it is I think a lot of PhDs just wouldn't want to work there because it's different. But that's awesome. It's cool to see someone with that level of educational background essentially do this kind of job.
I waited 16 years here at Browns Ferry, just in February. And so I worked for 9 years as a chemistry technician. I became a supervisor. And then 3 years ago, I went to transition into operations, which is a 2-year training program.
Yep, that's typical, especially for someone that wasn't in operations.
I've been a senior nuclear reactor operator for about 18 months.
That's awesome. Well, congratulations.
Thank you so much.
That's fascinating. Someone that's very experienced but hasn't had the SRO for that long, and that's a stepping stone for her career right there.
There's a lot there.
There is, yeah.
And she would have absolutely exceeded the requirements to do the direct or instant SRO. You really just need a bachelor's. You don't need a master's or PhD for that.
So how long will it take them to do the refueling in total?
Well, we break it up into small pieces. Browns Ferry actually holds the record at one point in time for a refueling outage of taking the vessel apart, changing out, putting it all back together. I think maybe 12 days. Bill can correct me. We have that.
That's impressive.
We have the record on that. However, this refueling outage is scheduled for about 30 days because when you shut a nuclear reactor down, you had to do all this maintenance that you can't do while online.
Yep.
So imagine driving your car. You can't change the tires while driving your car. You got to stop it, lift it up, change out the tires. So we're doing all that maintenance that we can't do while online.
Okay, so so that one's an outage.
Yes.
But this one's operating, right?
100%.
It literally is 100%.
Literally 100%. A nuclear reactor loves being at 100% and just hot, fast, and normal all the way.
And what's interesting is the scope for these outages are defined. I mean, there's various levels of scope definitions, sometimes 2 to 3 cycles ahead. And a cycle at Browns Ferry, like they said, is 2 years. So if you're trying to plan for something, say, 4 years in advance, you might be able to just squeak it in if it has to be done during an outage.
So I would have thought that I would be seeing something come out of there, but it's got a cap on it, right?
Well, so this is the spent fuel pool. Over here, where all that stuff is on top of it, are the shield blocks. And the reactor's kind of hidden all the way down there inside a dry well, and then the reactor head on top of it. So this thing right here,
the big sphere,
the big dome.
Okay.
That is the dry well head for Unit 2, and around the corner is the reactor head for Unit 2.
Have to disassemble all that
would
every
sit
time.
inside of it.
But we're not going to see that because that's in the C zone.
I don't know. Bill might be able to take you along this way in the clean area, and you might be able to get a view over there.
Okay, interesting. So the fact that you're refueling is the one time you get to see the reactors open. This is a very special time that we're here.
That's right. When you are riding this bridge and you're looking down into the vessel, it's really, really neat. It's just there. And you guys are here at a great time. The water's really still. We're not doing a lot of inspections right now, so you're going to have great views down into it.
Really?
Yes.
Do you have any recommendations of things I should look for if I'm going to get on the bridge?
Oh, I mean, you're going to look for the blue Cherenkov radiation. You're going to watch for how the people operate. So don't just think about the mechanics of it. Also think about how you're seeing people operate, how we work together as a team to make sure.
Yes, it's very different. The whole idea of peer checkers, step verifiers, independent verifiers, you don't see this anywhere else.
Safe, error-free,
and it's overkill.
Making sure communication is crisp and clear.
So the communication is very clear.
Always.
It's kind of like aviation where
And yeah, it is kind of like aviation. And the whole error-free mindset. Now, it's a term that's existed throughout the industry probably since the days of Admiral Rickover. But it's this one thing I've always had questionable thoughts about it, because having error in, just the word error in your step, even though it's error-free operation within the step, it just seems like it's very negative. It's like you're always preparing for the worst. I mean, and that is part of the job, but it carries a bit of a better not screw up kind of mentality that has good intentions, but can be a bit overkill sometimes.
A call and a call back kind of thing?
We actually have three-way communication.
Yes.
You send it, they say it back, and you tell them if it's right or wrong.
Really?
That's
yes.
right.
Okay, that's awesome. And
for everything, especially in the control room, and definitely on the refueling bridge.
The name of the lady that's the senior reactor operator?
That's Allison Vagoya. She and I actually were in class together, and her background, she's an engineer. She's providing direct oversight of the fuel handlers.
That's fairly common. They'll send a lot of freshly licensed people to do this job early. And when I say early, I mean relatively early in their history of getting their SRO license. I'm glad I didn't have to do it again because I just didn't want to hold it that long. It's a lot easier to get relief when you're in the control room versus when you're here on the refueling bridge. Maybe they for all I know, they do it differently. They stagger it every 2 hours instead of every 4 hours for when you and your partner hand off. But yeah, I had my senior reactor operator license between 2017 and 2022, and I'm glad I never had to do this.
And so Bill's here. He's going to tell you everything about it because Bill did my job before he changed into being a supervisor of INC. So he'll be able to tell you everything. He's ridden that bridge. He's done this job.
I have ridden the bridge though, so I got to experience the fun part of it.
Allison Admin's going to be providing oversight to make sure that we have no mistakes.
And that's mainly, you're required to ride the bridge as part of your licensed operator training. The plant I worked at, it was even required for reactor operators, which is interesting because reactor operators don't go there. Just senior reactor operators do.
Okay, so Sarah, I've got a question for you. So you've done all the stuff you've done. You're a reactor operator.
That's right.
You've moved fuel rods. Are you comfortable with a nuclear reactor in your backyard here in North Alabama? Like, do you feel safe?
100%. I have 3. I take.
That's the best response to that. Yeah, I've always felt quite safe around nuclear reactors.
When people are like, oh, there's a nuclear power plant, where? I'm like, oh, southwest of Athens. Do you like having electricity? 2 million homes. Like, I roll up into some place and they're like, what do you do? I'm like, I'm a senior nuclear reactor operator. You're welcome for the lights.
Yes. Yes. File out your tax returns. What's your job? You're welcome.
But you feel like it's all safe? Like, you know, people make mistakes. And I've something I've wondered about, like, if this is a man-made system and people made this and people do make mistakes, how do you know it's safe? Is it because of the procedures or operations, or why are you comfortable with it?
So we sweat the small stuff. I just corrected you on how to use a ladder. Did you think
She did, yeah.
Did you think that you were going to get told about a ladder? But that's it.
Awesome.
And we're always watching out for each other. Bill's like 3 levels above me, but he takes it as a piece of thing of I should have looked out for someone like that.
So it's culture.
It is.
It's culture. It's also robust design. So this is all about correcting the small stuff, like she said, but it's also so the design. I mean, it's a robust design boiling water reactor. That has multiple redundant safety systems to prevent you from the bad stuff that everyone's afraid of, such as core damage and fuel damage, or accidental radiological relief. It's the engineering robustness plus the culture is why it's one of the safest, if not the safest, industry in the world.
One of the great things about nuclear power is being able to raise concerns without the fear of retribution, and us knowing that we live here.
Yeah, there's no retaliation.
This is our home. We have to take care of it.
Tell me more about that, being able to raise concerns without...
It's called SCIWI. It's the Safety Conscious Work Environment. It's something that the nuclear power NRC mandates that we have.
Yes, and you get SCIWI training all the time, regularly. Not just from the Nuclear Regulatory Commission, but the Institute of Nuclear Power Operations, which officially they're a consultant group, but unofficially they're essentially a second, much more harsh regulator than the federal government.
If we had any concern, we can always bring it up. And if you don't feel that anyone is acknowledging your concern, you go to the next level.
Every nuclear power plant's required to have an employee concerns manager.
You have to do it anonymous. If you have to go straight to the NRC, you can.
Yes,
but
you can.
No one is going to turn you away on a...
The NRC also have an office there. It's the resident inspector, so you can go straight to their office. So yes, the federal government has an inspector on site all the time.
Conscious on a safety concern.
That's awesome.
Right.
Thank you, Sarah.
You're welcome.
Yeah, and you went to Mississippi State?
I did.
You didn't smuggle a cowbell in here anywhere, did you?
No, but it would be great if I did.
Okay, great.
So this is your core map, and it's got every fuel bundle location in the core. You can see the crosses. Those are where your control rods normally sit at.
How many fuel rods are there?
764 bundles in each core.
764.
That's right.
That is...
Yeah, bunch of little ones. Again, the planet I worked at had 193 bigger ones because it was a pressurized water reactor rather than a boiling water reactor.
Way more than I thought.
Yeah, there's a lot.
That's way more than I thought, okay? And you said the crosses are the cruciform control rods.
That's right.
Okay. And so okay.
A lot more control rods. Basically, it's around this. It produces around the same amount of power, but it's a bit more spread out.
This rod, how do I say this?
It's just an XY map, right? So that'd be rod 4732 is what we call it.
4732. And what is the unit?
Just core location.
Oh,
it's an arbitrary unit that we put up.
I see.
It's a grid. It's as arbitrary as playing a game of Scrabble. It even kind of looks like a Scrabble.
I see. Got it. Okay, so when we're out there, what are we going to see? Are they going to say, go get this rod and put it in the spent fuel?
Yeah, they'll say come into core location 1740, and then you'll have another guy agree with the location that they're going to go to the next control rod or the next fuel bundle. Then they'll go over that location, say we're on top of location, and they'll lower the mast to sit on top of the fuel bundle. Then they'll look to make sure that the fuel bundle and the location, the serial number we showed earlier, all that matches. Then once everybody concurs, the SRO will say, I agree, you can engage on the bundle. Then they'll engage, bring the bundle up, and then they'll talk to the next location they'll go in the spent fuel pool.
So who is doing that? Like, who's keeping up with what rods are moved when?
So there's a FATF that we have. This is what Jessica's keeping track of. They have a manual one on that bridge.
Okay, so she's the step verifier here, is what they call this outage position at the plant that I worked at. Note the official copy that this is the one that is going to go into the records for the plant. And yes, still uses pen and paper.
They've also got a...
Yep, and all those initials carry weight for all the operators and verifiers, because this stays with the plant for the life of the plant as a legal record. No pressure.
The bridge is automated now, right? So there's actually...
This information is loaded into electronic.
Yeah, so there's a computer on the bridge that'll help utilize to make sure that it's...
So Jessica, I noticed, can I see that mic for just a second? So these are fuel bundles moving from one location to the next?
Yep, it's showing them that they're going to pick this up from a reactor location, and then they are taking it to a location in the spent fuel pool.
So that's a location that means something to you.
Yes, this is where that fuel bundle, this is its home. And this is where it's going to rest.
I see. And it'll be there for 2 years or something like that.
Well, not necessarily. It could be going back to the core. It's just on this first fuel shuffle, this is where it's going to rest. It could be picked up and taken back at a later time.
I see. Okay, Bill and I are about to go up on...
And that's all going to be set by the core design team, which is typically going to be a corporate reactor engineer function as far as the core designers. They would design the fuel layouts for the entire fleet of nuclear power plants.
Bridge, which is a pretty big deal. He's getting our work order number.
Scroll down to RWP 92.
High red area, yellow.
Right?
Yep.
6250, we'll hit yes and yes.
All right. So that reset my dosimeter.
It did.
Yep.
Okay.
It's a different job, so that dosimeter is per work order. The other one that he has, the DLR, the dosimeter of legal record, that one stays active. So it reset it so it can take in the dose from this specific job. So the 0.1 millirem from the other job doesn't count toward this.
All right, then we'll come over here and we'll get dressed out.
I'm constantly thinking about where I set things down. All right, so I'm getting dressed now, right?
Yep.
It's good. Maintaining positive control of not only yourself, but of all of your equipment.
Thank you.
Justin, we don't wear our hard hats inside the C-zone.
Okay.
Where we're going, so you can take that off right now while we're getting dressed.
And that would have been some sort of evaluation was done by the safety team to say, hey, this hard hat is more of a hazard of falling in the reactor cavity than any possible head injury hazard in this particular zone. So a risk assessment was done by the safety team to determine that.
Thank you. Do I need the ear? I'm good without the ear pro for now?
Yep.
Okay, great. Christian's a smart cookie, isn't he?
Well, they all are.
Man, I wanted to... Everything got itchy all of a sudden.
Well, you got a couple more seconds. You can scratch yourself.
Can I scratch?
Yeah. You're not in the C-zone yet.
Oh, great.
Yeah. Scratch away.
Everything got itchy. So how do I look?
That's real.
Then
That's
hood over the top of this?
Yeah, hood over the top. You look pretty good. I got my dad. I got my TLD. We're good.
My TLD? Okay, cool.
All set to go.
It's all gone.
Validate. You ready to go?
Yep.
There it goes.
Validate your R on RWP 2520092.
Correct.
And your dose alarm is?
250. Dose alarm is 60. Dose rate alarm is 250.
Dose rate alarm is 250 milliram per hour.
That's correct.
So you are good to go.
When calling out numbers in the control room, it's important to say parameter value trends. I'm glad they've incorporated this for the radiation protection as well.
Thank you. So I need to take it out?
No. So it's right here against your chest. So what you'll do is you'll just
Okay.
when you get the green light, you go through.
Roger that.
Just like that.
Yes, sir.
Okay.
So y'all go try that out.
You ready?
I'm ready.
Alright, you got the green light, so you can progress.
I'm gonna hand this to you, Bill. Okay. Thank you.
If y'all have any questions, go to the F&B people, and there's another radiation protection technician inside as well.
Actually, I'll give that to
Yeah,
you.
when you go into these zones, you're going to see radiation protection technicians. There's going to be rovers that go around, and then there's some that are to the specific zones where a lot of the activity is going on.
Okay.
Yeah. Thank you. Thank you.
All right. You are in officially a C zone.
We're in the C zone, the contaminated zone.
That's right.
So this is the top of the reactor?
Make sure you hold the handrail.
Hey, hold the handrail, yes, sir.
This is actually the
Way to keep them straight.
drywall right here. This is the drywall cover. This right here is our FME buffer zone, right? These are our FME guys that are going to help us out to make sure that we can get on inside.
These are the monitors that keep a log of everything that you take with you when you go into the FMEA zone.
That FME buffer zone.
How y'all doing today?
Doing well. How are you?
Good. And then get y'all to sign this. Yes, sir. Please write as legibly as we can. Card and gloves.
Do you remember me saying the foreign material exclusion people wanted to make sure I didn't drop anything into the reactor?
Yes, this is
Well,
important.
to do that, it required a lot of straps attached to a lot of gear attached to me, and we even had to wrangle another guy to come over and help us make it happen.
Yeah.
You take the other one? Yeah, I'm gonna take this.
I've never seen anyone try to bring a camera into any FME zone before. This is a monumental, someone who is essentially a visitor coming in, and I really appreciate what he did. I based on everything I've seen throughout my career, I never thought I would see this happen. This is quite remarkable.
What's your name, sir? Philip.
I'm glad all these FME monitors and control personnel are willing to help him with this sort of stuff. That's great, because that would have been a convenient excuse just to tell somebody, no, that you can't come in here. It's too dangerous. The risk of dropped objects is too high. But they worked with them.
Phil's been with us for a long time up
Has
here.
he?
Now, by signing this paper, y'all acknowledge all the rules and requirements of the FME zone, correct?
Yes, sir.
Y'all have no loose jewelry, no earplugs on. You have chums on your glasses.
I do. Yes, sir.
Everything's
All right.
tracked.
Now, when y'all go in there, y'all understand everything that is going on the bridge and the work that's being performed.
Yes, sir.
Yes, and these are to remain on your wrist at all times.
Yes, sir.
All right, y'all understand everything you're doing to mitigate FME risk.
Yes, sir. I took the training this morning.
All right.
Yes, sir. Brian, right?
Yes, sir.
Thank you, Brian.
What we do once they get back.
I like how polite he is to all of these large numbers of support staff that you need to make this happen. That's just a class act.
Over spent fuel code, we'll acknowledge them, let them know we're coming in the bridge, and they'll tell us.
Okay, Philip, you're gonna be with us.
I'm gonna hold this and I'll hand it to you.
I'm just it's recording now, just letting you know.
Oh, you gonna put it?
So feel free to just point at places. If you find something interesting, feel free to point it, or don't.
And before y'all walk in, all we need to look at the bottom of your feet, make sure there's nothing stuck there.
Yep.
Yes, sir.
Important.
Tell me when you'd like to do that.
Right before you walk in, it's perfect for me.
Okay, so we're not in the zone yet.
We are in the C zone. We are not in that foreign material boundary.
Yes, there are boundaries for all sorts of things, and yeah, I'm used to seeing yellow or magenta as anything to do with radiation protection or contamination. Orange, I've seen white signs for FMEA zones. Or I guess FMEA zone is the plant I worked at. It was called FMEA, Foreign Material Exclusion Area. I don't see any here, but there is also green I've seen as a color for plant status control to avoid bumped components. And some of these colors might vary depending on what site you go to, but there's a lot of information about which particular hazard is the greatest of concern. And of course, right when you get above the reactor cavity, it's going to be for material exclusion.
Different levels.
That's right.
Yeah. Okay.
He's going to go over there and put it in the cleaner. Once he puts it in the cleaner, we'll have about 30 seconds. We're going to get on the cleaner.
Philip, what's your role here?
I'm a OST Boilermaker.
A Boilermaker?
Honest service technician.
He just talks like it's no big deal. This man disassembles the reactor vessel for us.
So he knows what he's doing.
He knows exactly what he's doing.
That is some highly skilled craft right there to do something like that, because that is a big piece of equipment. And there's a whole art and science towards detensioning something like a reactor vessel head. It's quite a marvel.
He's humble too.
He is very.
A lot of these guys
All right,
are. The best guys typically are.
Good. Good. Enjoy yourself, sir. Good.
Philip's enjoying this. So that's the reactor right there.
That's the reactor. We got waved
you.
on by the SRO? Go ahead, Destin. You go in front of me.
Yes, sir.
You got the chain? Thank you.
Hello. I'm doing well. How are you?
On the bridge.
Thank you.
We're at the cleaner.
Where would you like me?
Staying over here away from everybody.
Yes, sir.
So you're in a really
Makes
unique
sense.
spot. I have never taken anybody up here for this particular instance before. I've never seen this happen before.
This is a big deal.
I've never heard of something like this before. It really is.
It's a huge deal. So right now you're over the spent fuel pool. You can see we have coordinates. If you really look carefully, you'll see on the walls a map of where we're putting the spent fuel pool racks.
Over there.
Yep. Just try to be careful not to lean over the rails
pool?
with.
Can I swap with you, Philip?
Maintain positive control of your body parts.
So we just do it. How you want to do this?
Hand for me, and I'm going to hand you this, and I'm going to stay with you.
Okay.
You just keep that one around your wrist. I'll keep this one, and I'll stay with you.
Yes, sir.
Got everything around the wrists, and so when you transfer from one person to another, it's a solid plan. They made a plan for material
I'm gonna
exclusion.
We're pulling one out now.
No, they're washing one.
Now, hey, listen, that bridge will jar a little bit when it moves.
You're telling me it's going to move. Don't freak out.
Yeah.
And when it does move, hold on to everything because I don't want you to think.
Tell me when it's going to happen, please.
I can't promise I'll know that.
Okay.
When that fuel bundle comes up out of that, when that's sticking down in there, when it comes up out of there, it's going to move here in a second.
He's moving the bundle.
Now these are a bit smaller, but the ones at the plant I worked at, fully loaded, were a little over a ton. These are, they're going to be proportionally less than that, but still quite a bit of force that we're talking about here.
When it comes up out of the hose, see it coming up?
Oh my goodness, I can see that you're in cough.
Yeah. It'll come up to a safe height, and then they'll make it.
Lovely blue glow that you see when particles travel faster than light in water. You can't travel faster than light in a vacuum, but you can travel faster than it in water.
And put it in a fuel rack.
It's free right now. I can see it's out of the hole. Philip, was that a new?
The bridge speeds are going to be restricted as well, interlocked, based on how close the fuel assembly is to other fuel assemblies. It has sensors on there that you can only go above a certain speed once you're clear over open water.
Rod, or what was that?
That is an old one.
That's an old rod. How do you know?
Let me get on the other side.
You can tell how it's burnt. See the glow around it?
Yes, sir.
See the tops? They're shiny over there? Them's new ones. You can tell the difference because they'll be shiny like that all the way down.
Oh, okay. So
one thing about fresh fuel, there's no hazard. You can touch it, you can take it out of the water. The hazard is not the uranium, it's the fission products, and that is why these needs to be done well underwater. But new fuel receipt, which happens months before an outage, reactor engineers will inspect these outside of the water. I mean, they show up in big specialized containers, and they're typically brought in by truck.
They're shiny, meaning
they're all new fuel rods.
Those are brand new.
Yep.
These are all old. Well,
there's no fission products in a brand new fuel rod because no fissions have occurred yet.
a lot of this is empty, right?
Yes, that's where they're going to bring it out of the core and place them there.
So that blue glow I'm seeing is the Cherenkov radiation.
That is correct.
That's correct.
Yep.
I've never been more aware of my camera.
I'm glad.
And dropping it. Okay, what is he doing now, Philip?
He's putting place it in the fuel rack.
He's putting it in the fuel rack.
Yep. See it going down in there?
Yeah.
Most people think the radiation's green, but as you can see, it's not.
It's blue.
Yeah.
You think The Simpsons for that one.
Philip said most people think the radiation's green, but it's blue.
On all the shirts, it's green, fluorescent green. It ain't really true.
Philip, what's your story, man? I'm on level with you, man. You got an Alabama accent.
Yes, I do.
Where you from?
Been here all my life.
Been here all your life?
Yeah.
Okay. What just happened, Philip? They released
Just
it?
delatched it.
He released it, now he's coming up.
Is that a camera on the end of it?
It is. We got 2 cameras.
Are we going to the reactor now?
Yes, we are.
Can you turn around this way, Bill, and just face that way?
Yeah,
okay, right here.
Let me come through.
Oh, yeah, over.
Yeah, swap cameras with me.
Swapping cameras again?
I can't tell where this is pointing. I apologize.
That's okay.
So right now we're centering up to go through the cattle chute in order to get into the core.
Cattle chute. They have a name for everything. I've heard reactor containment buildings referred to as just a big round thing. But it's just it's a canal.
Holy cow.
You are now officially over a reactor vessel and refueling operations.
Oh my goodness. So that's a nuclear
I never get tired of that.
reactor. And they're just sitting there.
Well, those guys are doing their inspections with the camera. That's what they're working on.
Gotta do
they're
your
trying to get a camera down to inspect the welds on the
They're doing
on
what?
the vessel. They're working. We call it IVVI. They're doing inspections of the welds and all that type of stuff inside the reactor vessel barrel.
Really?
Let's get out.
There's a whole lot of
Sorry,
inspections that you can only do during an outage.
So now, Destin, they're going over a core location. They're going over a core location to pick up a bundle.
I'm gonna stay right here unless somebody tells me to move.
I already appreciate Destin's reverence for the plant. He's well, there's a reason why he's allowed to do this.
How is that?
I'm sure that was part of it.
I'd say probably somewhere between 80 to 100 feet of water.
So earlier, Sarah had talked about the importance of communication on the bridge. And I have been in environments like aircraft before where they do this call and response or the positive communication, but I didn't expect it the way it was happening on the bridge because there were so many people spread out and they all had different tasks and they were all being very clear about what they were doing. So it's like there was this tone on the bridge that was different. And I could feel that I was in the way, but I was off to the side. So they were like letting me be there with Philip and Bill. But at the same time, you could just feel the professionalism of the people around you. And of course, I wanted to be that way because we're literally moving nuclear fuel.
I mean, the term reverence is not a misnomer. I mean, it's very much a ceremony. It's like being in a church or a temple or something and people are doing something with the utmost reverence and respect for the amount of energy you are dealing with here. And it's one of the remarkable things about this industry that you really don't see very much everywhere else. Maybe a little bit in aviation.
In a reactor, which is awesome. Okay, this is footage from inside the pressure vessel. The reactor core is just down below us. This is what the team is actually doing. These are video cameras that are in the water with the nuclear reactor.
Interesting they're doing it at August. First I've noticed this. Yeah, that wouldn't have worked at the plant that I worked at, but maybe in the way that you stagger 3 units, that's where you end up. But yeah, at the plant I worked at in Texas, taking apart a reactor in August, man, that was not typically recommended.
It's not running right now, it would be boiling, but this kind of blows my mind that we're even able to see this. Let's take a look at what they're doing. Brownsbury's in the middle of a nuclear refueling outage, right? So they're moving fuel rods. This thing is called the Refuel Bridge Crane, or sometimes called the main hoist. This person is operating the hoist, which can go up and down and rotate on its axis. The hoist is connected to the whole bridge, which can move in X and Y. Now, at the end of the hoist, there's a couple of cameras and a grapple. The first camera is offset just a bit, mounted behind the grapple with a bit of a wide view. It offers context for the operator so that they know exactly where they are. The second camera is right on the end of the grapple, so the operator gets a close-up view of exactly the thing they're picking up, and they also get feedback on how the grapple is gripping the item. Let's watch them actually grab a fuel rod. Using a computer-controlled indexing system, the mast is automatically moved into the position that they specify with some type of coordinates that they typed in. They then fly in and they use the coaxial camera to verify they are where they want to be. They then approach carefully and look closely at the fuel bundle. Using the camera at the end of the mast, they then verify the serial number on the top of the fuel bundle handle, and then once they're satisfied with that, and everything's correct, they then lock onto the handle with a grapple. After they verify they have a solid grip on the fuel bundle, they can then extract it. They can then do any number of things with the bundle. They can use other cameras to inspect it. They can move it. They can rotate it. They can even put it in an ultrasonic cleaner. For every 4 fuel bundles that are in the
On the ultrasonic cleaner, at least at the plant that I worked at, you didn't typically do that every outage. It was within a certain periodicity of the individual fuel assembly. But every now and then, that's how you clean fuel assemblies.
reactor core, there's a control rod in the shape of a plus or a cross. It's called a cruciform control rod, and it's inserted from the bottom of the reactor. That's what stops the reaction.
And that's specific for a boiling water reactor. In a pressurized water reactor, the way you put it in is after the core is fully reloaded, then you put in the rods as inserts from the top. And they have latching mechanisms that you would put on when you put the head on the reactor vessel itself. It's quite the intricate process. I want to say this looks easier in the sense of doing it from the bottom versus the top when you're trying to put the head back on. But either way, it requires a lot of specialized outage personnel to pull this thing off without a hitch.
These control rods are so long, if they ever remove more than 2 bundles, that control rod could wobble. So to control this wobble, they have these things called blade guides. Anytime there's 2 or more bundles removed from a certain grid, they insert these blade guides to hold the control rod in position. If you look down into the core, you can see these bright, shiny spots.
There's all kinds of crazy tools. There's also essentially shoehorns for getting the fuel assemblies that are kind of on the ends. It gets
I thought
crazy.
those were new fuel rods, but they're actually blade guides. You'll notice that they're always in sets of 2. The operators say that inserting a blade guide is kind of like wiggling a pair of pants and trying to get the 2 legs to line up with 2 holes.
So there you have the difference. In pressurized water reactors, you're putting on shoes. In boiling water reactors, you're wiggling a pair of pants.
Pretty hard, they say. Now, while all this fuel rod movement is happening, there's this other team that Bill told us about, the IVVI team, which stands for In-Vessel Visual Inspection Team. They're using a bunch of cameras on jib arms. You can one of those cameras here, you see it's got a long arm and it can articulate. They use these cameras to closely inspect the mechanical integrity of the reactor vessel and any of its components. Watching them do this is so awesome, and it made me really respect the process that's going on here. Everything that's done has a crazy attention to detail about it, and it's clear that these nuclear industry workers really care about getting everything exactly right. Now that we understand what we're looking at and we know what they're doing,
and with stuff like this, if you get it wrong, it's going to bite you in the rear later on when you start having issues when you heat up, repressurize, and take the unit back online. So this sort of stuff is very important, and it's all about being proactive.
Just watch the team in action. They're about to take a rod from the reactor core, and they're going to put it over in the spent fuel pool.
I want to scratch my nose so bad.
Don't do it.
Here's a common nuclear industry joke. Where does Mr. T put the bad neutrons? In the spent fuel pool. There's a lot of dad jokes in the nuclear industry.
I will not. Philip, what's he doing, man? Did he just grab it?
Yeah, I think he's got one on there. Yeah, he's coming up.
Is that a light in the pool?
Yeah, we have cavity lights.
And he changed the orientation?
He did. He just rotated it back.
Does orientation matter?
Bridge is straight. Yes, orientation matters.
Why does it matter?
Oh, yes.
Because when you put 4 in there, you've got to have them orientated right.
And each fuel assembly is a little different than the other ones. So it's all about having a even neutron flux and heat flux profile once the reactor is started up and back up and running again. That's where the game of Scrabble comes in.
I can see the shrink off. So, Philip, that's called the cattle gate we're going through?
Cattle chute, yes, sir.
Cattle chute.
Yep.
Cattle chute. Got to make it even more Alabama.
Wow. Is that a hot rod?
It is very hot.
That's a very hot rod.
Yes. Back up out of the water, would no longer be here. None of us up there.
Really?
Really.
Yeah, you start getting it towards the surface, you're going to see area monitors go up significantly, and the evacuation threshold would be way before that thing comes fully withdrawn from the water. Also, there's interlocks in place to make it impossible to fully withdraw these things out of the water.
So the water's protecting us from the neutrons right now.
At least 6.5 feet or below.
So neutrons are not the primary hazard here because they're only a hazard when the reactor is operating. It's going to be things like beta and gamma radiation because, again, it's the fission products are the primary hazard of concern here. Neutron dose is only a concern when the reactor is actually operating because fissions are maintaining the neutron dose. A free neutron by itself, its half-life is only 15 minutes.
What they're doing now is verifying the location where they're putting it. They read the rack number. You can say they put it in golf. The big golf.
Yep.
Well, golf 11 is where they're putting it in.
Oh, I see.
See the numbers on the racks over here?
I see the letters, yeah. I'm going to watch him drop it, and then I'm going to look at his letters.
Yeah, numbers over here, letters over here. They keep up with the location where we put them. When we do a fuel dry cast, we'll put them in and know which ones to get.
They'll sit in the spent fuel pool for several years before they're decayed off enough that you would put them in dry cast storage for long term. And by long term, I'm talking at least a century.
So that was Golf 11?
The fact that he's able to capture all this.
So we were in Golf 11.
3 back, 13, 12, 11. Yep.
So now he's releasing.
Yep.
Clear.
Now they'll come up to safe location to get back to the cattle chute.
And on to the next one.
So we're in the refuel pool, And we're going to the reactor, right? We're going through the cattle chute now.
For most of my life, I
all slow, methodical, but like clockwork.
Understood nuclear power, but it was here, standing safely over the top of an open nuclear reactor with fuel in it, that I started to realize something. One of the main reasons people fear this technology is they don't understand it.
That's why people fear anything.
Everything was starting to make sense to me, and with that, I was starting to run out of things to be afraid of.
Thank you, gentlemen. No problem. Thank you, Allison. Don't want to hit that button.
What is it, the E-stop?
The E-stop.
Emergency stop.
That's awesome.
There's just a few more important things I want to show you, the first of which is in the equipment storage pool.
So what is this over here to the right?
That's your steam dryer.
And what is this?
That's your moisture separator.
Now, how does a moisture separator work?
Well, so it's essentially as the steam boils, it's got cylindrical, tortuous path for the steam, right? So only the superheated steam is going to make it out of the steam separator, and the remaining, I guess we'll say condensation, if you want to call it, the water, moisture content in the water will drop back down to the...
So it's almost like a still, but just for steam.
That's right.
Really?
That's right.
But it uses some of the energetic properties of steam to separate it.
Yeah, all it is really a big hunk of metal and lets the steam do the work.
Oh, really?
Yeah.
I see. Wow.
Yep, just provides a bunch of little steps through chevrons and little whirly thingies. Yeah. And the main reason for this is you want high quality steam, and by high quality, very little moisture content. One, it's more efficient for your thermodynamic cycle. And two, high moisture content at that high pressure and at that high temperature could impinge on the main turbine blades and potentially damage them over time. So it's about more efficiency and protecting the asset, the moneymaker, was what a lot of people in the nuclear industry refer to as the turbine.
Why is it in the pool?
Well, because it sits on top of the reactor.
Oh, that's right.
Because we boil inside the reactor.
This is another unique boiling water reactor thing. The steam separators are within the steam generators, which is not the same vessel as the reactor vessel. The reactor coolant goes and heats the steam generators, boils the water. Just a separate heat exchanger vessel from the reactor. The plant I worked at had 4 steam generators per reactor. But this one's a much bigger one that just goes over the reactor vessel.
And then we use that to make our steam high quality, and then we get it through the dryer and then out to the steam line.
So okay, I'm starting to understand. I had not considered this part of it. So you make hot water in there in the reactor. Yep. It boils, and it goes up.
Yep.
When it goes up, it goes into that.
That's right.
Mm-hmm.
And then is that like a heat exchanger? Like it bumps? I'm noticing pipes.
No, all they are like cylindrical pipes. There's no
ceiling.
It's
just to make it go in a direction.
That's correct. Okay. It's a tortuous path for the steam to go through in order to allow the moisture content to drop.
Yep.
I see. Okay, and so then that hot water gets circulated out, and then that goes to the turbine, right?
Steam.
The steam.
The superheated steam.
Yes. Yeah. Okay. So because the top is steam.
Right. You want as low moisture content as possible, right? Going to the turbine.
This gentleman come through.
Just a big dryer.
And I mean, it's not superheated very much. It's going to be just above saturation, just as it naturally flows out of there. But it's not going to be a huge pressure gradient we're talking here, or a huge temperature gradient, rather.
Big dryer filtration?
It comes up, it gets the steam drier and drier.
Really?
It was now time to exit the contamination zone and make our way over to the turbine, which I was super excited about. But first, we had to have all our camera equipment examined to make sure that no pieces had fallen off while we were on the bridge. While they were doing that, we took off our radiation protection clothing, and after that, we had to sign out of that RWP for the bridge and back onto the one that we had been on when we entered the plant. We then had to do some radiation testing to make sure we were clean, and Bill took us down and
essentially a combination of friskers and those monitors you see there to make sure that you're not contaminated.
See the turbine.
Back we came and then go in another elevator.
And you still have the gun.
You don't want to lose that.
Would you like to carry it?
No, not at all.
I would not.
So on our way over to the turbine, we had to go back through the room that had a lot of the control infrastructure for the control rods in it. We walked past that drain that we walked into when we went into the watertight door. We had to make sure we didn't step on the drain. And then we went through that watertight door and we ended up here.
Where are we, Bill?
We're on the turbine deck right now. And we're gonna
turbine deck.
Yeah, we're going to show you what the main turbine looks like. Typically, this is inaccessible when we're operating, right? You couldn't go to any of the other units. But this is our main turbine.
Is it in pieces now?
This is the turbine?
That's correct. 3-stage turbine.
And it's not running right now.
It is not running, that's correct.
So the fact that we're here is pretty cool.
Yeah, I think so. You got your high pressure turbine and your 3 low pressure turbine stages.
So this is the high pressure turbine, right?
Similar type of turbine to the plant that I worked at, and I imagine a lot of power plants that produce similar levels of megawatts.
That's right.
What's it wrapped in?
Just lagging.
For what?
Just to keep it cool or keep it in case somebody touches it.
Insulation?
Insulation.
Yeah. What did you call it?
Lagging.
Lagging.
That's
okay.
right.
Never heard it referred to as that before.
Cool.
Just insulation.
Following you, man.
All right.
So this is the high pressure side?
This is the low pressure side.
Low pressure.
We got 3 low pressure sides.
Wow.
High pressure being the one closest to the main steam line.
And so normally that thing's moving real fast, right? A lot of energy.
About 1,800 RPM.
So this is what keeps my lights on.
Yeah, this looks like the same
RPM
turbine.
is a lot for something
right.
this massive.
That's right.
So you have to
The one on the plant I worked at was actually on the roof, but it had additional layers of housing on the turbine generator building.
Because of rotational inertia. There's no way that you start with steam initially?
Yeah.
You don't have like a booster to get it going.
We have a jacking gear that will run it on. But
a transmission.
The turning gear, yes.
Well, effectively. Well, really the jacking gear just rolls. It's an electric motor that just rolls the turbine. So while we have steam getting ready to be applied to it, it doesn't blow the rotor. So
yeah, it's important to do that to maintain heating even. It's essentially just a really big hunk of metal, and you really don't want something like that to warp.
It's steam that rolls this turbine.
Wow. It's huge.
It's a lot of steam.
And so those lifting lugs are to take the top of it off. So is this a crane overhead?
That is, yeah. In some outages, we'll actually expose all this and show the turbine and have the low pressure turbine available, and we'll work on it.
So is there a turbine for each unit?
Yes, sir.
Which unit is this? Is unit 2?
Unit 2.
I guess there has to be because we're producing on the other ones.
That's right.
And these are big turbines. Sometimes you'll see smaller ones, so there'll be more than one for each unit, but this is typical just to have a really big one with multiple stages. And when I say a big one, I mean a series on one shaft. So the high pressure and 3 low pressure.
Sorry for the dumb questions. I'm overwhelmed.
Not at all.
So
no, look, they're not dumb. I mean, I could tell that the Destin is an engineer, just not specific to nuclear power plants. Aren't any dumb questions.
So this is Unit 2's turbine. Are the other Unit 1 and Unit 2 turbines in a different room?
They are very similar to this, mirrored to this, just inaccessible right now because they're operating.
What's on the other end? Is the generator down there?
That's the generator. Yep. So you can kind of see, actually that's a good view. You can see some of your pole pieces in the generator right there.
Oh, nice, they're working on it.
Wow.
Oh, that's a good view. Yep, and you see the signs that say FME area up there as well, and that's because, well, the generator housing and components are disassembled. You really don't want to have any foreign material in there, especially the sort that conducts electricity. Yeah, everything's going to be de-energized now, but you don't want to run into problems when you start the thing back up.
That's amazing, yeah, definitely. So in order to make a round thing run true, a lot of times you have an indicator that you put anchored to something else and you touch off. And then as the thing rotates, you can see if it goes up or down. I see one of those, but it's where it is kind of confusing me. So that's a dial indicator. Philip, have you ever worked in the turbine area?
I have.
Have you ever worked on that?
Let me see what you're looking at.
Okay. Yeah.
I have not.
I have.
Fair question.
That's great.
Yeah, I suspect they're checking bearing.
I can't say I've ever done the mechanical or electrical work where you get in and tear apart the generator, that sort of thing. Again, my background's in engineering specific to the reactor, and operations, emergency planning, that sort of thing.
Yeah, it's checking for run out on the shaft.
Say it again.
Checking for run out on the shaft.
What does that mean?
If the shaft were not perfectly round, then as it rotated, you would see a change.
A form of degradation.
That distance that they're measuring.
How do they turn the shaft? It's massive, so how can they turn it into this motor?
This motor right here. It has a worm gear on it. That worm gear will drive that gear you can see there.
Oh, it's interfacing right there.
Right.
Is that the jacking motor you were talking about?
That's the jacking motor, yeah.
Oh, wow.
Could get a bit closer, but they don't want to get into the FMEA without having to essentially tie everything back off, just like they did. Though this zone might be an FMEA 2, so not the same level of restrictions, but good to stay out of zones like that unless you absolutely need to go in there.
So this motor is specifically to turn the shaft so that they can test it.
A lot of measuring and testing equipment is installed.
That is so cool.
This is 2 different sections of the turbine shaft. So they've got their dial indicator set up as a reference on one, and they're measuring the other. They're looking to see that those 2 shafts are lined up.
So they will spin one relative to the other.
Right.
So this is the exact junction between the turbine and the generator.
Yes.
Got it. Is there a clutch or anything there, or is it direct bolted connection?
It's directly coupled.
Really?
Yeah.
And so when it spins up,
I even had someone at the plant I worked with that was surprised that that was all on one shaft, but it's a fair question. But little things you go over in training.
you guys bring up a unit, will you get any wobble or vibration?
There'll be some, but it's minimal. It's contracted out. There's a crew that balances this thing, and it's amazing how close they balance it.
Really?
So, at least at the plant I worked at, you get an alert when the vibration gets up to 20 mils. That's 20 thousandths of an inch. And the turbine will trip when you get up to 40 mils. I mean, after all, 40 mils, even that little of vibration on something that size, probably see the building start to shake a little bit. So that's why it trips at emergency, shuts down when you get to a point where the vibrations become excessive. Overall, not very much.
We spin this turbine, we keep very close eye on the vibrations on it. We're typically around 7 mils at worst.
Really?
Yeah, well said.
On any bearing. There's 12 bearings that are through here. We'll watch every single one of them.
Really?
12 or 7 mils is about where we get it.
That's amazing for something this large.
Yeah. Oh yeah.
Yeah. Where is it machined? Where do you buy a turbine like this?
This is GE's turbine.
Oh, General Electric. Do they own the turbine too, or they made it?
They made it.
They made it and you guys bought it?
Yes.
Got it.
I live in North Alabama, so we...
Yeah, they don't typically. Yeah, it'd be weird to see someone like that own a portion of your plant's assets.
Turbine. If I lived in the UK, we would say turbine. When it comes to making energy out of...
I've seen this in the comment section before. Yes, what I'm used to and what everyone has said to me is turbine, whether they're referring to a steam turbine or a wind turbine.
Steam, there's a lot of semantics that a lot of engineers like to get wrapped around the axle about.
Or wrapped around the turbine shaft about?
We're not going to worry about that right now. I recognize that like energy and power and all these, they have specific engineering units. But for now, let's just suspend all that and let's be kids talking about a really cool thing, okay? So the cool
roundy thing. Let's start with that.
About a nuclear plant is it makes steam. Like almost all power plants make steam. Steam is compressed and it's expanding if you allow it to, right? Well, we can use that. So I've got these little models here. These are little cheap little turbine blade things that I bought. And I've got one right here that's got a single turbine blade in it, right? And I've got this little valve set up right here to an air compressor. And
Simulate
if I turn this little
steam
valve
line.
right here, I can actually allow this thing to turn. Now this is a little different. This isn't expanding steam. It's just air running through this. So watch this. So I can create a gas that's moving into torque that turns a shaft, right? Now it's just compressed air. This is not expanding steam, but let's think about this for example. There's a lot of wasted air that's moving out of this thing, right? Well, what you can do for that is you can use multiple blades. So as the air comes in one side and it goes to the next one and the next one, if you have these multiple...
And keep in mind, at a power plant, it's not wasted. It's going to... The steam gets condensed and refed. I mean, you're operating in a cycle. There is a turbine that does exhaust to atmosphere. It was the Terry turbine because it's the manufacturer. It is a fourth string backup for the feed water system to provide it in the event you lose all electric power, basically the Fukushima type event. And there's also even more backups as well, but this one was installed when plants, at around the time the plant I worked at was built. That one will exhaust to atmosphere. At that point, the name of the game is you just want it to work no matter what. You don't want to introduce any complications like having it operate in a cycle that can potentially prevent it from fulfilling its safety-related function.
Blades stacked up, you can get more energy out of that gas. So I've got another valve here, so I can turn this thing.
Less air coming out.
Okay, get the idea. Multiple blades, I can get more energy out of the steam. So again,
and then you can extract steam from those and have that steam help preheat your feed water to make your cycle more efficient as well.
This is compressed gas, this isn't steam, but it's interesting. Now, let's look back at those images from those turbine blades that we saw earlier. This is a turbine blade from when Browns Ferry was first being constructed. You notice it's got like this bow tie looking shape to it. And then this is a turbine blade from a recent upgrade of the Unit 2 steam turbine here at Browns Ferry. You notice it looks like
shiny.
It's got
That's
little
cool.
things in the middle and then big things out to the side, right? In the middle, we have high pressure, and as it expands, it's like going to a lower pressure. You need a larger surface area on those turbine blades so you can act on it and get the same amount of torque, right? So that's why it's growing. If you look back at the actual turbine blades, you can see that the center shaft is solid, and the reason for that is that's where the steam is inserted. It's inserted right here in the middle, and then it runs along the fan blades out each end of the turbine. And the reason it's a bow tie shape is actually fascinating. In my little model here, I've got a single turbine blade, right? You see that? So watch what happens when I apply the air. It's actually going to try to push it out. So watch this flywheel push to the side. You ready? See it? It's very subtle. And watch again. So it's actually trying to push out of the journal bearings here, so they mirror it, and that axial thrust is canceled out by the axial thrust in the other direction. So they flip the turbine blades on each side, which is fascinating. Now, Bill said there are 4 turbines in that building, 1, 2, 3, 4, and one seems to be smaller than the others. Let me show you how this works. So we have, in the reactor that we saw earlier, we have neutrons, right? Uranium-235, and these neutrons are in water in a very special way in the reactor core, but they're making steam, right? And they're making that steam at 1,000-something PSI, but it's coming off of that at like 900-something PSI after it goes through some valves and stuff.
Yeah, something less than 1,000, sure.
And so, 900.
It's flowing in that direction.
And what happens there is they take that steam and they put it in a high-pressure steam turbine, right? So it goes into that bow tie thing, kind of like we were talking about earlier, but this is the high pressure steam turbine. Now, as it goes through that, it goes through the middle and it expands out. After that, you've got this other steam that's coming out of this thing. It's like 250 PSI, but it still wants to expand. So what they do is they take more steam turbines and they put them in the same room.
Use as much
now these
as
are
you can.
low pressure steam turbines, okay? So they take this 250 psi steam, and then they put it on all the different low pressure steam turbines like this. So you can take that and you can run them in parallel paths. So you've got this thing you've built now where you've got uranium making steam, and you're pumping 900 psi steam into the high pressure turbine, and then out comes this 250 psi steam, and there's other things going on.
Interesting he mentions that. So that 900 psi number, the first stage impulse pressure is another way of measuring reactor power. There's a few different ways. One, you can just look at neutron flux and radiation detectors by just the amount of neutrons you're producing. Another is the heat, the number in megawatts that's being produced by the reactor, and also the number of megawatts going on the grid by the generator. And another is the impulse pressure that you are imparting to the first stage of the main turbine. I say the first stage because anything else will be affected by various losses of going through any of these lines he just drew. But the first stage is going to be the one that matters for determining what the reactor is doing. And then there's another one. It's known as the secondary calorimetric, which is basically a heat balance equation. And that one is typically going to be the most accurate. But you look at multiple versions of them just to see what you have going on. But yes, there's a lot of different ways to measure reactor power.
Like separators and condensers that we're going to talk about right now, but these lower pressure steam turbines, they're bigger. And the reason they have to be bigger is because they're at a lower pressure. And if you're going to act on a lower pressure on a larger surface area, you can end up getting the same force because pressure is equal to force by area. You get it. You're smart.
It all comes back to force equals mass times acceleration. Pressure is the same thing, but in 3D.
What's going on here? So if we have all of these turbines on the same shaft, and then we put a generator right there at the end, voila, we have a nuclear power plant. We've gone from hot rocks making steam, and that steam can go to making torque, and then we're putting all these different turbines on the same shaft. It's really cool, by the way, how they balance the torque along this. I think that's fascinating. Well, maybe we'll talk about that later. All that goes to a generator here, and you get electrons out the other side. So nuclear power to electrons.
Neutrons to electrons.
Fascinating. So
that one guy said.
Turbine, high pressure turbines, low pressure turbines, generator.
So high pressure side, low pressure, generator. Is that right, Bill?
That's right.
Okay. So, dumb question. Why is the high pressure upstream? So does the steam run down as it goes?
It's lower quality steam on the low pressure side.
But it doesn't run along the turbine. It runs in and out.
These are actually steam valves, CIVs down here, so it'll actually run in and out and under the generator.
Got it.
Or under the turbine, excuse me.
Generator.
This is an operating generator. So the generators.
Interesting, you can get relatively close to the generator, but not the turbine. I'm curious why it was set up that way at this plant, because you could get to the exterior housing of all of the things at the plant that I worked at.
From here to the wall over there.
It's just hard to hear you.
That's fine. The generator's from here to the wall, and this is what's generating that 1,350 megawatts electric that you saw in Quinn's office earlier.
Yeah, so that meter in Quinn's office coming right off of this.
That's right.
That's cool. So it's quieter than I thought.
Yeah, it's not too bad. It's a little loud.
So what did we see in the other room? You said we couldn't go in that room normally.
The turbine. So that's the turbine that spins the rotor. It's got a common rotor.
So the turbine's that way.
That's right. So three things to make electricity, right?
Yeah.
Rotating element, magnetic field, current carrying conductor, right? So you got whole pieces inside this generator. You got a magnetic field on the rotor that's spinning, cutting lines of current down to the generator, down to the isolate buses out to the grid.
So this thing right here is what makes 60 hertz power.
Yes, it is, absolutely.
So, like
60 hertz is grid frequency, and it's obviously you're producing power from the grid. It is important to match your grid frequency.
How do you synchronize this to the grid?
That's an excellent question. So happening is this is running at a certain speed, right? And I always like the phrase nuclear power equals 120 times the fun, right? That's an equation for us. NP equals 120F. The speed of the machine times the number of the poles is equal to 120 times the frequency, right? So what we're able to do, what that really means, is frequency is directly related to the speed of the machine. So I can control the speed of this machine before we're synchronized to the grid to make it come up a little higher. If you think about your ice cream going for 3 days AC, right? Yeah. We can make it come up a little bit faster, and then we'll synchronize the grids. And we have this thing called a synchroscope. And it'll spin around, and when it's at 12 o'clock, it means the phase from the grid and the phase from the generator are synchronized, and we'll close it.
That happens right here.
Well, the breaker's down below us. They do it up in the control room.
Yeah, you do it in the control room, and the way I was taught is when you sync the generator, so the reactor operator has their hands on the main generator output breaker, they're watching the synchroscope, and you go slow in the fast direction, watching it go like a clock. He says at 12 o'clock you're matched, which is true, but like he said earlier, you pick up a little bit of the grid first. So while it rotates, you typically close it right when you see the synchroscope pass 11:55, and then you immediately start raising power to make sure you're going the correct direction and you don't reverse power the generator, which would kind of convert it into a big steam pump and could result in some damaging torque being applied to the generator shaft. So it's a very important operation. It's just as critical as starting up the reactor itself is syncing the main generator output breaker. That is something that is trained on in the simulator extensively and just in time. It's known as just-in-time training for when you send the operating crews who are going to be doing it once you come up from the outage to perform the operation of syncing the main generator to the grid.
What's outputting the energy into the grid.
As we headed to the exit, I was just struck by how much Bill knows and how complicated this plant is, and I asked him about that.
There's a lot of things to know here.
There are.
Is it intimidating for you?
I think I saw it once in the comments section. Somebody said all roads lead to a nuclear power plant. There's a lot of multidisciplinary things that you need to know. And so from the jobs that I've had more specific knowledge in the reactor itself and more general knowledge, the sort of things that you get during SRO training of everything else when it comes to components like turbines, steam generators, backup diesel engines, that sort of thing. I didn't have much knowledge about the other components when I was in college. It wasn't until I started working at the nuclear plant. And it wasn't really until after I got my SRO license that I was able to get that much knowledge about the inner workings of the plant. But a lot of it is breadth more so than depth. There are people at the plant that I work with that know way more about valves or diesel engines than I ever will, because that's some of their specialization. And it's really about all these teams working together that give you the wonderful product that is a nuclear power plant.
When I first got into nuclear power, it was very intimidating. I had to study really hard, but the more and more you work here, the more and more you understand what's important, the easier it gets. You know, everybody has their little piece they understand too, right? That's about working as a team. Somebody knows better than somebody else.
Yeah, he's kind of saying the same sort of stuff.
Even when you think you know everything, I promise you don't. Yeah. Nobody here knows everything.
That is why I say what I say at the beginning of every video. I don't claim to know everything nuclear.
The last thing we had to do was exit the radiologically controlled area, which meant we had to make sure we didn't have any radiation contamination on us, which I thought was going to be pretty easy. So we took apart the camera gear and handed it over to be checked, and we failed.
Oh, come on, these screens. 4,500.
Is that a lot?
No, it's too high. Here, let's put your other one in over there.
Put this one in?
It's kind of the center there.
Got to be careful about how many tools you put into each individual monitor. These are tool monitors that check everything you brought with you.
All right, hopefully we'll get at least one camera out.
So we went back and we cleaned everything, gave it a really good wiping down to have it rechecked, and we failed again.
It can be a pain. depending on what you
Possibly
got and where you were.
Possible radon gas.
This was most likely that radon that's emitted naturally, and the fact that the testing machines are so sensitive they're picking it up.
George and I are slowly.
Another example of nuclear overkill.
The camera's out. Bye, little camera.
Well.
Yeah, cook it. Almost.
We ended up disassembling the cameras because things could make it out if they were smaller physically for some reason.
Separate tool monitors
So once we disassembled everything and made sure everything was cleared to go, we passed.
Yeah, we made it.
Now that we had officially left the RCA, logged out of our RWPs, and turned in our dosimeters, we started to make our way out of the secure area.
A big thank you to Bill, Angela keeping us safe, Philip, thank you Clarissa, thank you George. I can't point at George because there's stuff that way. Thank you for visiting us. Thank you very much. Bill's got.
This was very eye-opening that he was able to do something like this. Props to everyone, not with Destin's team and everyone who works at TVA that was able to do something like this. Thanks so much for watching, and thanks so much for the recommendation.